Imagine you work in a startup company as a system administrator, and it is your job to make sure everything runs with no issues. The workload you usually operate consists of backend, data ingestion, and databases with extra layers of data processing. The company operates with small teams, where usually one person assumes multiple functions, so it is very common to see developers doing data modeling, project managers developing code, or DevOps managing databases. Recently, customers are complaining about the system being slow, and after investigating, you noticed the database is reaching its limit, causing a bottleneck. After doing research, you realized that the same database is being used for absolutely everything, from storing streaming data to running analytics, and from storing syslogs to as well as customers' data. It did not take you long to reach the conclusion that the data architecture is operating in a one-size-fits-all approach, and that it needs to be broken down into separate components to develop a more mature data administration strategy. Does that sound familiar to you? Because it sounds very familiar to me. This is a typical scenario where a data lake would really help, so you come with a plan to save the day. Since the workload runs in the AWS cloud, why not explore AWS data-related services to separate storage, data ingestion, analytics, real-time analysis, and even machine learning, breaking that monstrous database into components that do the right thing for the job. I like to call this a divide and conquer strategy. Isn't that a cool term? And that would be absolutely better than using a single server with lots of storage. Adding a data lake to this architecture could help solve many issues by using the right tool for the job, and rest assured that if you don't know how to start with data lakes, you came to the right place. The goal of this course is to equip you with the knowledge needed to understand what exactly a data lake is and how to use AWS data-related services to create and operate a data lake in a secure and scalable way. After completing this course, you will understand why data lakes are such a buzzword in the market and why everybody is doing it. I would like to welcome you to the first week of Introduction to Designing Data Lakes in AWS. In this week, you will learn about the value proposition of data lakes, their characteristics and components, and how a data lake compares with databases and data warehousing. To warm up, we will also discuss some sample data lake architectures at the end of the week. So let's get started. Alright, now that you are familiar with what you will learn this week, let's better understand why to use data lakes and explore its components. As mentioned in the previous video, it may be the case that you have an enormous database or data is distributed across multiple databases. Neither scenario is good. With the first one, you may have load issues. In the second one, data cataloging and security may be challenging. Although some data lake solutions may sound like a very powerful database, that is a common misunderstanding. We avoid comparing data lakes to databases because data lakes encompasses multiple functions in the data spectrum, such as data ingestion, processing, machine learning, data visualization, and other components. The additional reading of this week has links comparing databases and data lakes in a more detailed way. The main reasons to invest in a data lake are to increase operational efficiency, make data available from departmental silos, lower transactional costs, and offload capacity from databases and data warehouses. Databases usually have its storage and processing mechanisms tied together, making it less flexible to scale storage without processing and vice versa. We will talk a lot about this aspect in this course. On the other hand, a data lake is a centralized repository that should allow you to securely store all your structured and unstructured data with no scaling restrictions. One of the most significant advantages of a data lake is storing your data without having to think about its structure. And that's where the name lake comes from, being organic information just like nature. Let me give you an example to illustrate a scenario where a data lake is instrumental. Imagine you have an e-commerce website where you are informed that sales decreased 10% since last Friday. You realize that last Friday, the front-end team applied a deployment that changed some elements in the payment UI. If you had ingested the user clickstream data, such as mouse coordinates in your website, you can get this raw data and plot a heat map with data visualization tools. At a high level, this could allow you to see if users are struggling to find the buttons in the front end because they are trying to locate those as they were placed in the old interface before the deployment. This is an example of raw data transformed into an insight, And this is precisely the type of thing that data lakes allows us to have. The most meaningful insights today are generated from transactions, weblogs, click streaming, social media, and Internet of Things, or IoT devices. As you may expect, the volume of data produced by those is pretty high. Needless to say, they are better suited for storage services that are dedicated for storing data. By decoupling storage from data processing, you can use different data processing and data visualization components that look at the same data, and that's another advantage of data lakes over databases or data warehouses. Now that you know the value proposition of data lakes, let's talk more in depth about their main characteristics. The first aspect I would like to cover about data lakes is that they should be data agnostic. In other words, data lakes should not be limited to store just one file type or data structure like usually a database do. Efficient data lakes allow you to store all kinds of data, such as pictures, data text in multiple formats, compressed or not, encrypted or not, audio, video, binary files, and everything else. As I said at the end of the previous video, being data agnostic and storing raw data gives you the advantage of using a more appropriate data processing tool to generate insights. Let me give you another example. Think about a web-scale e-commerce platform with operations all around the globe. With the information collected regarding package fulfillment centers, business users may want to use that data to generate reports that will lead to insights about sales during holiday seasons, while other departments may be interested in using that data to train machine learning models that will suggest improvements to fulfillment center logistics and operations. Those two insights are different in nature from each other, but they can be possible if those different teams have the data available and cataloged in a data lake operating efficiently. In a nutshell, data lakes allow you to dive in anywhere in the vast data collected to generate insights. We usually say that another characteristic of mature data lakes is the fact of being future-proof. Let me better explain this. Being future-proof here usually indicates that you may not have a business question today, but if that business question arises in the future and you have data around that topic, the answer can potentially be right there. With the use of the right processing and data visualization tools, you can generate insights that can help you a lot. If you identify with the scenarios mentioned here, you surely need a data lake. With correct data ingestion, cataloging, and processing to keep it organized, it will be delightful to extract insights from it. There are two kinds of processing involved in a data lake, which we will discuss further in this course. First is the process made before or while ingesting data. Second is process made after data has been stored. This process includes, but is not limited to, cleansing, aggregating, enriching, merging with other datasets, and much more. Let's continue the data lake journey, learning about the data lake components in the next video. Alright, let's talk more in depth about the four main components you would like to have in your data lake architecture: ingest and store, catalog and search, process and serve, protect and secure. Let's start with ingest and store. A data lake is not a mature data lake without proper data ingestion mechanisms. Because data lakes are data agnostic, this may be challenging because you need different technologies to ingest different data into a central location. Let me give you some examples to illustrate what I mean. Imagine a company with a fleet of 100 trucks, equipped with IoT devices like this one I have on my hands. Let's say the devices are equipped with GPS antennas and mobile connections providing the truck coordinates every second. When this data is submitted, the system should provide truck's location in real time to its users. If you do the math, with 100 trucks providing data every second, you have 6,000 data points per minute, 360,000 data points every hour, and way more than 1 million data points just during business hours. This requirement may need data ingestion and storage solutions operating at a minimal latency on a large scale, which clearly is a challenge, especially if you don't use the right approach. In this race for the lower latency, a better ingestion layer likely uses data streaming technologies, such as services from the Amazon Kinesis family or Amazon Managed Streaming for Apache Kafka. We have videos for you to learn more about Amazon Kinesis in further weeks of this course, so we got you covered. Perhaps we could use a different data ingestion mechanism if the requirements were different in this scenario. If we did not need to provide near real-time insights to users, we could think about using an ingestion mechanism that consumes data in batches and not streaming. We also have videos for you to learn about data ingestion in batches by using managed AWS services. The second fundamental component a data lake must have is data catalog and search. Let me talk about it. Mature data lakes provide efficient indexing and searching mechanisms to quickly discover what data is stored and where. Have you already heard the term "don't let your data lake turn into a data swamp"? The term data swamp here is an informal way to represent data lakes that are disorganized in terms of data cataloging and searching. Data lakes can and should reach a high level of organization and catalog with the help of databases. Regardless of whether the database is SQL or NoSQL, it is very important to have a quick and secure way to find your data when you're looking for something. The third component data lake needs to have is a processing layer. Some people in the data community advocates for using Hadoop as an end-to-end data lake solution. Using Hadoop that way may sound perfect because you have data storage, while at the same time you are ready to go in terms of data processing, right? Well, let me throw some thoughts around that. Apache Hadoop is a very popular big data technology that gives you the ability to store and process data using servers configured with open source software. Since a Hadoop cluster has processing and storage tightly coupled, when you allocate servers to use Hadoop, you end up paying for both storage and processing. One of the main components of cloud computing is paying for what you use and nothing more. So if you just want to use Hadoop for storage, you may be paying for processing power while not using it. That does not mean Hadoop is not used in data lakes. They play a big role, and data lakes would not be a thing without it. But it makes more sense to use Hadoop only when we need to process something. That's why a cloud-native data lake uses dedicated storage services that only charge you for storage and nothing else. You can use cloud storage services like Amazon S3, which tends to be cheaper and more durable because there is no processing involved. Typically, in data lakes when you need to process something, you can spin up what we call a transient Hadoop cluster, do the processing, store the data back on S3, and then turn off the cluster. In addition to that, separating compute from storage gives you another benefit, which is the ability to use different compute and storage layers using the right tool for the job while optimizing for cost as well as performance. AWS has a service called AWS Glue, which executes Hadoop jobs on demand where you only pay when there is a job running. I don't want to give spoilers about what's to come on next week, so let's focus on the fourth and last component data lakes should have: protection and security. A mature data lake should provide all the components mentioned so far in a secure way with configurable permission mechanisms that prevent unauthorized users from accessing the data. Using AWS managed services gives you the ability to manage things like data retention, encryption, access control lists, and refined governance standards. We won't be focusing that much on this topic in this course because our primary goal is to understand how to create and operate a data lake at scale. Although, there is a video talking about security on the last week of the course. Earlier, I mentioned the term data warehouse. In this video, I will tell you what a data warehouse is and how it compares to a data lake. The Wikipedia definition of data warehouse is a system used for reporting and data analysis, which is considered a core component of business intelligence. Data warehouses are central repositories of integrated data from one or more disparate sources. According to that description, and what you have learned so far regarding data lakes, you may think that they are the same thing just with a different name. They are not, and let me explain the differences because although they sound like the same thing in theory, they are different in practice. A data warehouse is usually a database optimized to perform analytical queries that leads to insights. But because it usually operates as an analytical database, you need to create tables and define the table structure before adding your data into your data warehouse. When you create those tables, you have to set the table columns and data types. In other words, a data schema that generally needs information to be structured. When the schema needs to be populated and it needs to be determined before you write the data, you have what we call a schema-on-write architecture. Although schema-on-write is good for data normalization because it would reject data that does not fit in that specific format, it is not ideal for flexibility, which is where data lakes really shine. Data lakes are what we call schema-on-read, and that's the first fundamental difference between data lakes and data warehouses. Data lakes can handle unstructured data and mainly operate in a schema-on-read fashion, which means that you do not need to concern with the data schema while ingesting the data to your data lake. That allows you to take care of the schema only when read data for some future processing, hence the name schema-on-read. As you're going to see later in this course, AWS has a service called Amazon Athena that allows you to match the table schema to your dataset and not the dataset to your table schema. An Amazon Athena table does not store data on itself. The tables are mostly metadata pointing to where the data is, and we commonly use Amazon S3 for that. With that being said, if something changes in terms of data structure in S3, you can change the Athena table to match that change. Typically, we end up creating another table in Amazon Athena. I'm not trying to pick a winner between schema-on-read or schema-on-write systems. I'm just defining that a data lake uses schema-on-read and data warehouses use schema-on-write. Having a schema-on-read on your data lakes gives you the flexibility that you need. Another difference between data lakes and data warehouses is that data warehouses mostly use the SQL as the language for querying. That limits what you can do, and some engines even support the creation of user-defined functions and other functionalities to extend that a little bit. Although that is good, having a custom compute framework based in a programming language like Spark and Python gives you more power and flexibility because if you have statistical data, you can use compute frameworks that are exclusively focused on statistics. The same applies with machine learning, computer vision, and other needs that you may have for your data lake, allowing you to reuse the right tool for the right job. Another difference is that while data warehouses work with structured data only, data lakes work with unstructured and structured data natively. Since data needs to fit in a table in a data warehouse, you have to normalize and pre-format that data to fit that table, and that limits you on the type of data that you can store in a table in your data warehouse. Now, one thing is for sure. Although data lakes and data warehouses are not the same thing, they should be used together to extract valuable insights. It is very common to see architectures ingesting data to the data lake first, then cleaning and storing that data using data lake tools, and then storing that data into data warehouses that uses data visualization tools. Some data warehouses may work faster because they work with structured data. That's it. I hope this video helped you to differ data lakes from data warehouses and when to use one versus another. In the next video, we are going to review some typical data lake architectures, and remember, there's no better approach. It all depends on your needs. Now that you are one step further into the value proposition of data lakes, and you are more confident on talking about the differences between databases, data lakes, and data warehouses, let's take a look at some data lake architectures. I'm going to start simple and then extend the example with more elements providing more flexibility. It is always a good practice to sketch and draw the architecture diagram with the AWS services involved before creating the resources in your AWS account. That gives you a good plan of what comes ahead and helps you present your idea to other people in your organization. Let me introduce a scenario and explore some diagrams briefly talking about the AWS services involved. Imagine you have web servers you control where you want to get insights out of the access logs produced by them. This simple architecture can help you achieving that. You can install on the servers an open source tool published by AWS called Amazon Kinesis Agent. Amazon Kinesis Agent continuously sends data to Amazon Kinesis Firehose, a data ingestion service which you will learn more about next week. Kinesis Firehose can easily store incoming data in S3. Once the data sits in S3, it can be queried with Amazon Athena by doing SQL queries, and that's how you want to extract your insights, such as detecting HTTP errors after deployments or so. Now, this is a very minimalistic data lake that was designed to meet a specific goal, which in this case, it extracts insights out of web servers. I like to call it a made-to-order data lake, which is a data lake that was created to fit a single specific purpose. This made-to-order data lake is ideal when you have total control on how you are producing the content, which in this case is the web server logs. The reason I'm saying this is because once you have control over how you produce the data, you can produce that data in a format that is already friendly for the system that is consuming, which in this case is Amazon Athena, requiring zero to low data processing to fit the consumer needs, because you can prep the data before sending. You may still need to do some data cataloging, because as your dataset grows, finding things in S3 may be challenging, and you may also need to think about access controls of who can do those Athena queries and who can reach this S3 bucket. Now, let's say you're getting noticed in your company because of the success of your Athena queries and the insights you're getting out of it. With the success you are making with your made-to-order data lake, other teams came to you asking if they could send their web logs as well. But now, you do not have control over how that data is being produced because the web servers belong to other teams. That's where you need to start thinking about a more generic data lake solution that could fit different use cases. A workaround to keep this data lake simple is to trigger an AWS Lambda function each time data is uploaded from Kinesis Firehose to S3. These Lambda functions are code that runs in response to events in AWS services, being useful to transform data as they come. You could create different Athena tables pointing to the new dataset, but if you want to make use of the same queries made by your original table, you can use Lambda to do some data transformation that removes unnecessary fields or convert data from one format to another. Lambda functions are typically used for things that do not require intense compute power, like file renaming, text parsing, field normalizations, etc. With the ability of transforming data as you store, you reach some level of modularization in your data lake architecture. As you can imagine, your solution is going well, and it is a matter of time for more people asking to store and ingest data in your data lake, and more people asking for other ways to search and visualize the data you are ingesting. Remember the conversation about using the right tool for the job? So, you can add some extra layers in your data lake that would allow that to be achieved. For instance, you can extend the ingestion layer to API Gateway to receive HTTP posts for producers that cannot use Kinesis. That would make more flexible for the data producers. You can also plug Amazon Elasticsearch, which is a full-text search database that can find content easiness. Elasticsearch comes with a plugin called Kibana that helps you visualizing data in forms of charts, heat maps, geospatial maps, and much more. Can you see that as you make your data lake more generic, you extend the capabilities of what people can do with it? One last consideration that it is important to highlight is to understand that although a data lake involves multiple services, you don't need to use all those services at the same time with the same degree of utilization. That's where cloud computing really shines, because you pay only for what you use. I'm saying that because it may sound overwhelming to see some complex data lake architecture diagrams using tons of services for data processing, cataloging, and ingestion, but after you have some understanding of what each service do, it doesn't become overwhelming. We plan showing you how to use and operate these AWS services during the next week to help it making less overwhelming for you. Stay tuned and stay with us.
Hey there, it's me, Morgan. Welcome to week 2 of the course. Last week, you learned about some of the fundamental concepts of data lakes. This week, we will start exploring the different AWS services used in data lake solutions. Different services will be used for different use cases, and it's all about knowing first what your use case is and then finding a technology to fit, not the other way around. AWS has a wide variety of services that you can use when building out your data lake, and we will spend this week getting familiar with a handful of them. In future lessons, we will dive deeper into the services and how they work specifically. But for this week, we are going to focus on learning the basic functionality and use cases at a high level. Please remember to read the class notes as you move through the lessons and use the discussion forums to ask questions. Data lake architectures on AWS can be complex, and you will use a number of AWS services as building blocks to make your data lake. Because AWS builds services in a modular way, it means architecture diagrams for data lakes can have a lot going on and involve a good amount of AWS services working together. It can be a bit hard at a first glance to digest these diagrams, but don't worry. We will explore the main AWS services that make up a data lake and break down those complex data architectures into concepts that are easier to understand and remember. Think of the services that compose your data lake as belonging to one of three categories. The first category is AWS services used for data storage and cataloging. A data lake has a few key components. It stores and secures data at an unlimited scale. It allows for structured and unstructured data to be stored together. It catalogs and indexes data without data movement. And it connects data with services and tooling for analysis and processing. So, what AWS services can you use to enable these key factors of a data lake? We will cover that with the AWS services used for data storage and cataloging. This category focuses on the services used to build the data lake itself, not the services used to populate the data lake or analyze the data in the data lake. The next category of services we will cover is the AWS services used for data movement. Once you know what services you are going to use to build out your data lake, how are you going to ingest data into that data lake? Well, you have to move the data from its origin or source into the data lake so it can then be indexed and made available for processing and analysis. There are multiple AWS services that support data movement in a general sense, and the services that you use are entirely dependent on your use case. The last category of AWS services we will cover are the AWS services used for analytics and processing. When you get to this part of the course, you will have an idea of how data is moved into your data lake and what services are used to properly index and catalog it. The question then becomes, when and what services can you use to process and analyze data? You might want to run SQL queries on the data, maybe join multiple datasets together to feed into a dashboard for visualization, or even use the data to generate things like business reports. We will cover multiple AWS services you can use in this category, and just like the data movement category, the AWS services you use are heavily dependent on use case. When you look at a data lake architecture, remembering these three distinct groupings of services can help break it up into a more manageable concept. First, you have the storage and cataloging aspect. Second, you have the data movement aspect. And third, there's the analytics and processing aspect. There are benefits to thinking of your data lake as having decoupled layers like this. It means you can manage and scale and secure each individual building block for your data lake independently. Keeping compute and storage separate from each other is a very powerful concept that you should keep in mind as you continue through the course. We will also take some time to talk about interesting and innovative ways that you can use your data lake using AWS services like machine learning for predictive analysis. This topic belongs to the AWS services used for analytics and processing category, though this course isn't designed to dive deep into machine learning. You will still explore from a high level what is available and hopefully get inspired to learn more about how data lakes can play a role in machine learning. In this video, we will go over the first category of AWS services used in data lakes. Let's begin with storage and cataloging. Because we are talking about data lakes, you know you are going to have a lot of data. You could have thousands of terabytes of data that you need to store. And you know that you will need to use services that will scale up as your data set grows, as well as allows you to store both unstructured and structured data together. What options do you have? Initially, you might consider storing your data in a relational database, since databases can be both indexed and queried. But as you already learned in an earlier lesson, this is not feasible. Wouldn't it be nice if there was a service that allowed this schema on read model to work while also having built-in scaling features that make hosting a data lake easy? Amazon Simple Storage Service, or S3, to the rescue. S3 and S3 Glacier are the preferred AWS services for the storage layer for your data lake. Let's talk about why that is true. The first factor to discuss is that you can store any type of file you want. The storage layer should be data agnostic, and this is a key element of a data lake. The data shouldn't exist in silos, where data of one type is stored separately from data of another type. Everything should be in one centralized place. S3 has the concept of buckets that allow you to store contents of any type together with no limit on the total bucket size. Which leads me to my next point, scaling. S3 is a service where the underlying infrastructure hosting the service is managed for you. This is great because as you need to store more data in your data lake, S3 just handles it. There is no need to set up scaling of any sort with S3. The next feature that makes S3 a loved service for data lakes is its impressive durability. S3 is designed to provide 99.999999999% durability for your objects over a given year. Now, that is a lot of nines. What this really means, in a practical sense, is that if you upload an object to S3, the likelihood that that object would be corrupted or lost over time is incredibly low. That makes it a great candidate for data lakes, because you will collect the data under the assumption that while it isn't being used currently, it will be used in the future. Another key component of a data lake is that the data is made accessible for tools and services to process and analyze the data. Most AWS and commercial solutions already know how to work with S3 as the data layer. On top of S3 being scalable, durable, and offering integrations for analysis, it also has some specific features you can use to help bring down the cost of operating your data lake. S3 offers different storage tiers that allow you to categorize your data into different cost tiers based on how frequently it will be accessed. The way it breaks down is, if data is accessed frequently, you can use a tier that will charge less for the requests made to access the data, but charges more for the storage of that data. If data is accessed infrequently, you pick a storage class that charges more for the requests, but less for the storage. Don't worry too much about these storage classes, just understand that they exist and you can use something called intelligent tiering, which will monitor the data access patterns for your objects and assign the storage class that makes the most sense for you. One more point on data access patterns. You can also take advantage of Amazon S3 Glacier and S3 Glacier Deep Archive. This is for objects that are not being accessed regularly and therefore can be archived. The data stored with Glacier incurs the lowest storage costs available, and although it provides a lower cost per gigabyte, there are fees associated with the retrieval time. This is a good option to store data that currently has no known use case, but you could make a use of it in the future. It's also nice to use for historical data that isn't being used anymore, but you want to keep it around for various reasons. Check out the class notes for more information on these different storage classes. All right, so long story short here, Amazon S3 is the storage layer of choice for data lakes hosted on AWS. This is one piece of the puzzle. Now, let's briefly talk about cataloging and indexing data stored in S3 for your data lake coming up in the next lesson. Let's continue the discussion on AWS services related to storage and cataloging. One of the main issues organizations run into when trying to create and operate a data lake is they might find that they have a large amount of raw assets, but the users of the data lake aren't really sure what that data is or even how to find out what data exists for them to begin analyzing and processing. On top of that, data will be transformed over time. Keeping track of the changes to the data formats and the versions of the data can be confusing for users when it isn't properly managed. They aren't sure if the data they need is in the data lake or not. This means that the data, though it exists, is not very useful. It's unorganized, it's dark and murky, it's not visible. It's more like a data swamp. When the data is not easily turned into insight, you might have a data swamp. How do you fix this data swamp problem? Proper metadata is the first step. Metadata is data about the data. So why is metadata useful? Let's consider a library. When you walk into a library, there are thousands of books. How do you know where to find the book that you are looking for? Well, libraries have systems in place to help you search for the book you need via its metadata, like the title, ISBN number, or author. You need a similar way to catalog your data in your data lake, and look no further than the service AWS Glue. AWS Glue is a fully managed, serverless data processing and cataloging service. It has many features we will cover in this course from a high level. But the one to focus on to solve our lack of metadata is the central metadata repository called the AWS Glue Data Catalog, and it is a drop-in replacement for Apache Hive Metastore. The AWS Glue Data Catalog consists of tables, which are the metadata definition that represents your data. A table consists of a schema, and tables are then organized into logical groups called databases. You used what is called a Glue crawler to populate the AWS Glue Data Catalog with tables. A Glue crawler is triggered to sort through your data in S3 and calls classifier logic to infer the schema, format, and data type. They will construct a data catalog using existing classifiers for popular asset formats, like JSON, for example. But you also do have the ability to add your own classifiers or choose classifiers from the AWS Glue community. This is useful when trying to recognize and catalog other data formats that aren't supported by the built-in crawlers. The generated metadata from crawlers is then used to help you understand your data, and it is used in the authoring process of your ETL jobs. Beyond crawlers, there are other ways to populate your metadata catalog, and you should check out the class notes to get more information on that. AWS Glue eliminates the need to manually create and define schemas. You can even configure your crawler to update the data catalog if the schema of the data changes or is deleted, as well as compare versions of your tables to track the data changes over time. Once you add your table definitions to the Glue Data Catalog, they are available for ETL jobs and also readily available for querying in other AWS processing services. This is another main component in maintaining a beautiful and valuable data lake. You will learn a lot more about AWS Glue as the course progresses, so stay with us. Before we hop right into the next category of AWS services for data lakes, think of a real lake. How did the water get into that lake? Or in other words, how was that lake formed? Is it fed by a small but consistent stream of water always flowing in? Is it fed by a large waterfall that pours thousands of gallons of water into the lake per minute? Or perhaps it was formed by water that used to be glaciers thousands of years ago, but now it only gets filled by occasional rainfall. Or maybe it's a combination of sources that fill the lake. Let's take this idea of how literal lakes get their water and apply it to the concept of a data lake. The data in a data lake will likely be coming from multiple sources, and the way you move or ingest that data will depend on the source and the type of the data that you are ingesting. Consider how a stream feeds a real lake. There's a small amount of water consistently and constantly pouring into the lake with a steady flow. Now, think of your data lake. Maybe you have a data source where you have to constantly ingest small pieces of data to fill the data lake. For example, imagine you have water passing through a pipe, and you put a sensor in the pipe, and this sensor measures the temperature of the water and sends the data to be ingested and then processed. This is an example of ingesting real-time data, or ingesting streams of data in motion. You can use a service from the Kinesis family for real-time data ingestion. Kinesis has multiple AWS services that allow you to ingest data streams of various types and analyze that data in real time, moving data into AWS in a secure and scalable way. The first service to know about under the Kinesis family is Kinesis Data Streams, which Rolf did touch on briefly in a previous lesson. This could be used for our water pipe device example. Kinesis Data Streams is used to collect data from various sources, and you can then build Kinesis applications to continuously process the data, generate metrics, power live dashboards, or send aggregated data into stores like Amazon S3. To use Kinesis Data Streams, you have to use the AWS Software Development Kit, or SDK, for Kinesis, and process the incoming data, which is organized into shards. You are responsible for scaling these shards in and out as needed. The data stored in the shards can be processed by one or multiple consumers, all using the SDK. If you are not a developer type and you don't want to worry about using the SDK or think about what shards are or how to manage them, you can instead use another service under the Kinesis family called Kinesis Firehose. Kinesis Firehose ingests data from sources in real time, just like Kinesis Data Streams, and allows you to simply designate where you want that data stored. There is no need to use the SDK. This makes it easier to use Kinesis for simple use cases that don't require data processing or aggregation before storage. Rolf will talk more about Kinesis over the next week. Now, not all of the data in your data lake will be there from real-time data ingestion. Let's say you would like to ingest data in a RESTful manner. For example, when you are working with IoT devices, you will likely want the device to transmit data that you can collect. IoT devices are often microcontrollers with limited hardware capabilities. Given these constraints, using an SDK like the Kinesis SDK could work, but it might be simpler to use standard HTTP calls. HTTP libraries are lightweight and can be loaded easily. So, what AWS service can you use for data ingestion that would allow an HTTP call or even WebSockets? Look no further than Amazon API Gateway. Amazon API Gateway is a service that allows you to host APIs that act as a front door or interface to a backend. This backend could be an application running on an EC2 instance, or an AWS Lambda function, or even another AWS service, like Kinesis. By hosting a RESTful API with API Gateway, you can ingest data into your data lake by simply submitting HTTP calls from your data source with the data posted on the payload, without needing to use any specific SDKs or heavy libraries. API Gateway can be a simpler alternative for data ingestion, but it doesn't offer the same depth of features for ingesting stream-like data into your data lake with a service like Kinesis. What you choose to use really depends on your use case. There are often use cases where you need to ingest data from third-party sources that you do not manage or have control over. Depending on what your goals are, third-party data might enrich the data that you have already collected. For example, let's say you are a company that creates software for healthcare services. You might be interested in collecting anonymized data from healthcare providers or data processors that you can store with your own data in order to gain insights. Instead of trying to curate this data yourself using physical media or managing FTP credentials or integrating with different APIs, look at using the service AWS Data Exchange. Data Exchange offers an interface to hundreds of commercial products from data providers across many industries, like financial services or healthcare or others. You can use the Data Exchange APIs to securely extract and deliver the relevant data into your S3 destination. Now, what about data that is generated by the use of a third-party software, but it's data that you do own? For example, data that comes from tools like Salesforce or Google Analytics. You might think that you need to write your own connectors to these services to get the data provided by this SaaS application into your data lake. The good news is the service AppFlow can handle a lot of this for you. AppFlow does the data collection and secure transfer to your data lake for you without you needing to write your own custom connector code. You can run data transfer flows on demand, on a schedule, or after an event. You can quickly analyze this data using services like Amazon Athena to join it with multiple other datasets already stored in S3. You can also use pre-curated datasets through the Registry of Open Data on AWS, which makes it easy to find datasets made publicly available through AWS services. You can consume data being hosted through this program, and you can even apply to share your own datasets. Sharing data in the cloud lets users put focus on analysis and deriving insights. To wrap this up, just like real lakes that are formed in various ways or are formed in a combination of ways, your data lake on AWS will be formed by data coming from various places, and the tools that you use for data ingestion will vary as well. You can use a service from the Kinesis family for real-time data ingestion, Amazon API Gateway for RESTful data ingestion, AppFlow for data ingestion from SaaS applications, Data Exchange or the Registry of Open Data for public data sets that you want to ingest into your data lake. At this point in the course, you know what services are generally used for data storage and data movement. But what about data processing and analytics? You'll certainly want to actually use the data once it's been ingested and stored. In this video, we'll be talking about which services you could use for processing and analytics at a high level. First, let's discuss the idea of transforming data. It's common to need to tweak data in your data lake before analyzing it, because you might find that the data you are ingesting is not in a very useful format, or perhaps the data includes things like line breaks that your tooling can't handle, or the data is dirty and full of errors like duplication or missing fields. You might want to process your data in batches or as the data comes in from stream ingestion live. It depends on the use case. Let's focus on the idea of processing data in batches first. To process data in batches, you can create scripts to fix errors, reformat, or otherwise process the data after it has been uploaded into your data lake. Using a Hadoop cluster for this data processing is common. Apache Hadoop is an open source framework that is used to efficiently store and process large datasets ranging in size from gigabytes to petabytes of data. Instead of using one big, powerful computer to store and process the data, Hadoop allows you to cluster multiple computers together to analyze massive datasets in parallel quickly. Let's say you have an existing Hadoop cluster in place, and you've been using this on premises. And now you want to shift to using AWS, using the same tooling in order to minimize refactoring. In this case, you can use Amazon EMR. Amazon EMR is a managed cluster platform that allows you to process and analyze the data from your data lake. Unlike infrastructure constraints of on-premises clusters, EMR decouples the compute and the storage, giving you the ability to scale each independently by using S3 as the storage layer. Amazon EMR is great for processing data in batches because it allows you to process massive amounts of data in an efficient way. And it's likely that you will be working with massive amounts of data in your data lake. With EMR, you can create long-running or transient clusters. The benefit of a transient cluster is that you can spin up a cluster and then it turns off when your processing job is complete, only paying for what you use. In contrast, persistent clusters continue to run after data processing is complete. If you determine that your cluster will be idle for the majority of the time, it is best to use transient clusters. For example, if you have a batch processing job that pulls your web logs from Amazon S3 and processes the data once an hour, it is probably going to be more cost-effective to use transient clusters to process your data and then shut down the nodes when the processing is complete. So, although EMR manages the Hadoop cluster for you, wouldn't it be really nice if you could just run your processing jobs without worrying about the configuration and management of a cluster? This is where the service AWS Glue can be handy. You already know about the AWS Glue data catalog, but it has other features that you can use in your data lake. I mentioned in a previous video that Glue is a managed ETL tool that makes it easier to categorize your data, transform it, enrich it, and move it reliably between various data sources and data streams. You know about the classifiers and the crawlers, and that you can use the output created from the Glue crawlers and classifiers to run your ETL jobs. But let's talk more about what this really means. AWS Glue has a concept called jobs. Jobs are the business logic that is required to perform data processing work, the type of work you would do with an Amazon EMR or Hadoop cluster. With Glue jobs, instead of creating a cluster to run your processing logic on, you instead provide a set of configurations. A job is composed of data sources and data targets, which come from the tables created in the AWS Glue data catalog. It also has a transformation script, as well as other customizations that you provide. This job is run on a schedule or triggered by an event. The job runs and transforms or moves your data, and Glue will do all of the orchestration and management of the underlying infrastructure that is needed to run your data processing logic. Think of it as serverless Hadoop. Amazon EMR will give you greater control over the entire process, but Glue Jobs is a very convenient tool. We will dive deeper into Glue later on in this course. Now, let's explore another option for processing, with a focus on real-time data. Let's imagine you are collecting data in real time using one of the Kinesis services, either Kinesis Data Streams or Kinesis Firehose. The data you are collecting is raw data, and it might not be in the best format for analyzing. In this scenario, you want to transform the data as it comes in, instead of running processing jobs or processing it in batches. What options exist for this use case? The first service that comes to mind is AWS Lambda. AWS Lambda is a serverless compute service that runs on demand based on triggers. Kinesis Data Streams is an available trigger for your Lambda functions. This allows you to pre-process the data before sending it downstream to its ultimate destination. Now let's talk about some analytical tools you can use once your data is processed and in a format ready to be consumed. You can use various tools to analyze data depending on the data itself and your desired outcomes. Consider this example. The data you want to analyze is in CSV format and located in S3. Let's say you want to run a SQL query against this data. You might be tempted to run a process to load it into a relational database and then run your SQL queries. However, with AWS, you actually don't need to do that. Let's talk about Amazon Athena. Athena is a great serverless service to use with your data lakes because it allows you to query data in S3 using standard SQL, similar to how you would with a relational database, all without needing to move or load the data into a database. You can query the data directly out of S3, which allows you to run ad hoc queries against your datasets. With Athena, there is no need to manage a cluster or data warehouse to run your SQL queries. Athena integrates with AWS Glue, as it natively supports querying datasets and data sources that are registered with the AWS Glue data catalog. These sorts of native integrations are one of the reasons AWS is a great choice for operating data lakes. The different AWS services work together as building blocks to form your solution. Another AWS service that integrates directly with S3 for analytics is Amazon Redshift, the data warehousing service. Redshift allows you to spin up clusters to run complex SQL queries for analytics against your data. You can load data into Redshift from various sources beyond S3, which gives you the ability to run joins across datasets. Athena and Redshift are great for analyzing data that has already been stored in S3. But what if you want to analyze data as it comes into your data lake in near real time? For example, imagine you have IoT devices sending seismic activity to AWS for analysis, sending 60 data points every second, and you are ultimately storing this data in S3. In this scenario, let's say you have tens of thousands of devices, ingesting the data and running analysis on it, say in batches once every hour, with the goal to generate an alert when the data points exceed a defined threshold. Well, if you want to alert people that an earthquake might be coming, running this analysis once an hour won't be good enough. You need a way to detect anomalies in real time. Well, as you might have noticed by now, when I say the words real time, I'm most likely going to be talking about Amazon Kinesis, which is the case here. You can use Kinesis data streams or Kinesis Firehose for real-time data ingestion, but you can also analyze that data in real time using Kinesis Data Analytics to do things like generate real-time dashboards. The service enables you to quickly author and run SQL code against streaming sources to perform time series analytics, feed real-time dashboards, and create real-time metrics. You can process and analyze streaming data using standard SQL. This would work perfectly for our example of IoT devices sending seismic data, as you could query the data as it comes in, and if the values exceed normal thresholds, you can then send an alert via simple notification service. The other great thing about Kinesis Analytics is that you can configure destinations for where you want to send the results of your analytics. So, if you want to generate a real-time dashboard for the incoming data, and then also save it to S3 or elsewhere, like Amazon Elasticsearch Service for search capabilities, that is all possible using the Kinesis family of services. Speaking of Amazon Elasticsearch Service, or Amazon ES, let's go over what that service is all about. Amazon ES is an open source search and analytics engine for all types of data. That data can include text, geospatial, structured, or unstructured. You can send real-time data into Amazon Elasticsearch Service, but it also supports using data from S3. One common way to use Amazon ES is to use it for log analytics, since it's great at indexing full text log data from various sources to make it queryable and discoverable. Amazon ES is very commonly used in the Elasticsearch Logstash Kibana, or ELK stack, which can give you a robust suite of add-ons to ingest, store, and visualize data. Visualization is a great way to wrap your head around the data that you have collected, aggregated, and analyzed. Kibana is a supported visualization tool through Amazon ES, but AWS also offers Amazon QuickSight for visualization, which we will cover in a future lesson. All right, lots of information in this video. The main takeaway is this: everything is entirely dependent on your use case. Sometimes it can seem like different AWS services do basically the same thing, but each AWS service has its own strengths that are tailored to specific use cases. Those strengths may or may not play well with your use case. Make sure you dig deeper into each service before deciding what you want to use for processing and analyzing data in your data lake solution. Though we won't dive deep into this topic, this video will highlight what is possible with data lakes on AWS. Machine learning can be used for a wide variety of purposes, and one use case is predictive analytics. For example, one common predictive model is called forecasting, where you analyze historical data to try to predict future outcomes. Let's say you're a large online retailer selling apparel, and you want to use machine learning to help drive your inventory levels. Based on the amount of clothes you predict you will sell, you will stock that much inventory. Or maybe you're a company that is offering online content streaming, and you want to use machine learning for a recommendations engine, where an algorithm will suggest new content for the user to consume based off of their previous preferences. Beyond the use case, you might be wondering, how does machine learning relate to data lakes? Well, in order to train a machine learning model to do prediction, classification, or other types of machine learning, you need lots and lots of data. It's common to store training data in a data lake and integrate with AWS services to use the data for machine learning purposes. Data lakes help you collect, store, prepare, and categorize the data. And because it operates with using a schema on read model, it gives the ultimate flexibility for machine learning developers and data scientists. Depending on your skill set and your goals, you might be looking at integrating machine learning into your applications in different ways. You have options where the machine learning services are managed and the hard work is done for you entirely. There are machine learning platform services where a lot of the hard work is done, but it still requires some deep knowledge of machine learning to get the outcome that you want. And then finally, there is the do-it-yourself option, where you do all of the hard work. If you are a machine learning expert, you can use the data in your data lake to train your own models and use your own algorithms. You will likely be using EC2 instances for your compute power. AWS provides AWS Deep Learning AMIs, or Amazon Machine Images, that make it easier to build deep learning models and build clusters with machine learning and data lake optimized GPU instances. If you want to dive deep into machine learning, but you don't want to manage your own environment, check out Amazon's SageMaker. SageMaker is a platform service that makes the entire process of building, training, and deploying machine learning models easy by providing everything you need to connect to your training data, select and optimize the best algorithm and framework, and deploy your model on auto-scaling clusters of Amazon EC2 instances. And finally, if you want to use machine learning algorithms, but you don't want to develop and train your own models, you can use plug-in, pre-built AI functionality directly into your apps via APIs. AWS provides solution-oriented APIs for computer vision and natural language processing, like the services Amazon Recognition for image and video classification and Amazon Comprehend for natural language processing. For example, maybe you run a photo hosting website and you want to use machine learning for classification purposes, like identifying objects in photos that get uploaded to your site. The objects that get detected could be used for accessibility to generate the alt text for the images. This alt text could then be used by screen reader devices. The service Amazon Recognition would be great for this use case, as it provides tags for images or videos based on what it recognizes in the image. Those tags can then be used to create the alt text. When integrating machine learning into your applications or using the data in your data lake alongside machine learning, the service or approach that you choose entirely depends on your use case. It also depends on how much control you want over the entire process. Some services are more convenient to use and require less expertise, but give you less control. whereas other services require more expertise and work on your side, and therefore they are less convenient, but they also give you the most control. On the control side of the spectrum, you have Amazon EC2 and the deep learning AMIs. This is the do-it-yourself option, and it gives you the ultimate control, but also requires that you have the most knowledge. In the middle is Amazon SageMaker. This allows you to focus on the algorithms that you want to use without really needing to manage the environment. So you get a good amount of control, and you also get a good amount of convenience. Then, on the convenience side of the spectrum, you have services like Amazon Rekognition and Amazon Comprehend, which are really plug-and-play services. They give you access to the machine learning models that are pre-trained through APIs. So it's super convenient, and it requires the least amount of work, but it also doesn't give you a ton of control over the algorithm itself. Now that you know some of the different services to build out and use your data lake, let's think about how you can put them all together. It can be an involved process to get your data lake ready for use in AWS. You could, of course, go through and provision and configure all of these services individually, like Amazon S3 for storage, AWS Glue crawlers and classifiers for crawling and categorizing data into the Glue data catalog, AWS Glue jobs for transforming data, and then using tools like Athena, QuickSight, or EMR for analysis and visualization of the data. That could take a long time, and you might not be ready yet. So, instead of going through and provisioning each individual AWS resource and then configuring them all to work together to form your data lake, let's talk about the service AWS Lake Formation. Lake Formation automates many of the manual steps that are usually required to create data lakes. These steps include collecting, cleansing, moving, and cataloging data, and securely making that data available for deriving insights. The way this works is you point Lake Formation at your data sources, and then you crawl those sources, and it moves the data into your new S3 data lake. From there, Lake Formation then manages AWS Glue crawlers and AWS Glue ETL jobs, the data catalog, the security settings, and the access control. After the data is securely stored into the data lake, you can then use your choice of analytical services, like Amazon Athena, Amazon Redshift, or Amazon EMR. You can create your own custom crawlers and classifiers to use through Lake Formation, but Lake Formation also supplies blueprints that you can use. A blueprint is a template that enables you to get going quickly to ingest data into your data lake. There are several blueprints you can pick from, each for a predefined data source, like a relational database or AWS CloudTrail logs. Blueprints take the data source, data target, and schedule. Once you choose a blueprint, you can then create a workflow. Workflows consist of AWS Glue crawlers, jobs, and triggers that are generated for you. Workflows run on demand or on a schedule. When a workflow is initiated, you can view the status of it directly in the AWS Glue console. If you need more customized data sources, transformation processes, or tooling in place for your data lake, you can always build it out manually yourself. AWS Lake Formation can be a great tool to use to get started with data lakes on AWS. It makes it easier to put all of the building blocks together for a solution. However, you need to understand that Lake Formation is not a data lake itself. It's a service that helps you orchestrate all of the different pieces and parts that make up your data lake, like S3 and Glue. Once you need further customization for your data lake, you might choose to do everything step by step with each individual AWS service. This is a walkthrough for exercise 1, creating an Amazon OpenSearch service cluster. So the context for this exercise is that you are working at a company that is measuring the temperature of water in lakes, ponds, and streams around your area. And you have sensors that's taking these measurements and sending data every 15 minutes. And we want to collect this data and put it in a data lake. And then we want to be able to search and index and catalog this data. So we're going to be using services like API Gateway to ingest the data, a Lambda function, Amazon S3, Amazon OpenSearch Service, and also a couple more. So before we can dive right into this exercise, let's first create the IAM roles that we're going to need. So to do that, let's first navigate to the IAM service, select IAM, and then from here we can click roles on the left-hand navigation, then click create role. Under use case, we're going to select Lambda and then select next. So this is going to be the execution role that the AWS Lambda function uses. So we're going to go ahead and click next. And now we need to attach some permissions. So first I want to attach a permission to allow full access to Amazon S3. And then I want to attach a permission for Amazon ES, which I'm going to retype that, make sure I can actually spell it right. All right, there we go. So now we can have Amazon ES full access. This is for Amazon OpenSearch service. So then I'll go ahead and click next. And then we need to give the role a name. So for this one, let's call it Data Lake Week 2. And then we can see here, we can see the trusted entities, which is going to be a Lambda function. And then we can see the policies that we've attached. And I'll go ahead and click create role. Now we can see that that role has been created. So next, what we want to do is we want to create an Amazon OpenSearch service cluster. So you're going to use OpenSearch service for cataloging and indexing the water temperature. So before you can start ingesting documents into your OpenSearch service domain, you have to first create it. You could also use AWS Glue for cataloging your data, and we'll explore that more in a future lesson. But for now, let's go ahead and navigate to OpenSearch service, select Amazon OpenSearch service, and then let's click create domain. And let's give the domain a name, water temp domain. And then we can scroll down here under deployment type, we'll click development testing. And then we want to make sure we have the latest version selected, which we do. Now, if we keep scrolling down here for data nodes, I want to change the instance type to be a T3 small search. And then you can see here it's giving you a little warning that this is only suitable for testing and development purposes, which is what we're doing. We're just exploring, learning, so that's good for us. So then we can scroll down some more. And then for network, I want to change this to be public access. And then if we scroll down, I'm going to disable fine-grained access control. And then I'm going to, under access policy, I want to change this to be configure domain level access policy. And what this is going to do, this access policy is essentially a resource policy for this domain that controls whether a request is accepted or rejected once it reaches the OpenSearch service domain. So you could either have an IAM ARN be allowed here. So for example, an IAM role, like if you have an IAM role that's trying to send a request to OpenSearch service, then you would need to include that here. But what we want to do is instead select an IPv4 address, so an IP address. So for this, you would need to navigate to whatismyip.com, and that will give you your IP address, and then you will replace the IP address in the star with your IP address, and then change the action from deny to allow. So this will allow your IP to post to this domain. So if you click on JSON here, you can then also see the JSON policy here. So we want to allow all actions to OpenSearch to this water temp domain as long as under the condition that the IP address matches my IP address. So now we can go ahead and scroll down and then we can click create. Please note that it can take up to 15 minutes for this OpenSearch service domain to be created. So we will go ahead and move on to the next task for now, which is going to be creating an S3 bucket. And then we'll come back to this in a little bit and see how it's doing. So let's go ahead and navigate to S3. And then we need to click create bucket. And our bucket name needs to be globally unique and DNS compliant. So I'm going to go ahead and type data lakes week 2. And then you would need to make sure that you're using something that is unique here. So I'm going to go ahead and put my initials and then the year, and hopefully that's unique enough. We will see. And then we can go ahead and make sure that the region is the region that you're trying to use, which for me is going to be US East 1. and that is also the region in the instructions. And then we can scroll down and we can click Create Bucket. Now we want to make sure that we remember this bucket name because we will be using it in future steps. All right, so now we have an S3 bucket that will be the storage layer for our data lake. In a later task, we're going to modify the bucket access policy so that the Lambda can actually write files to this bucket. And we'll learn about bucket access policies in future lessons, but what it is essentially is another resource policy that will control whether requests will be accepted or denied based off of a principal. So again, a principal can be something like an ARN from an IAM role, things like that, maybe an IP address, it could be an account, an IAM user. So we'll go ahead and edit that later. But what we want to do right now is create the Lambda function. So let's go ahead and navigate to the Lambda service, select Lambda. And Lambda is a serverless compute service. So what we want to do is we want to upload our code for our function, and then the function will run in response to incoming requests. So this Lambda function will capture data that is on the payload of the incoming request, and then it will upload a JSON document to S3. The Lambda function will then upload the document to OpenSearch service as well. So we're going to go ahead and choose Create Function here. And then we want to select Author from scratch. Then under function name, I want to put Upload Data. And then I'm going to select the latest version of Python, which is Python 3.9 right now. And under permissions, we can expand change default execution role. And then we want to say use an existing role. And then we want to select that role that we created earlier, Data Lake Week 2. So we'll select that. And then we can click Create Function. Now the Lambda function code will need to be uploaded for this. So what we're going to do is scroll down here to the Code Source tab. And then I want to click Upload From, and then I want to select a zip file. Now we can upload the zip file that we had downloaded from the first step. Now I've selected the Upload Data zip file, and I'll go ahead and click Save. All right, so now what we need to do now that that has been saved is we need to scroll down to the runtime settings, which is right here. And then what we want to do is click Edit, and then we want to change this handler here. So the handler is where the function execution will begin, and we need to make sure that the handler that we define here matches the handler name in the code so that it knows where to invoke that function. So I'm going to go ahead and change that so that it matches, which is going to be lambda.handler, and then I will click Save. Then we want to choose the configuration tab here, and then we want to select environment variables. And what we need to do now is edit the environment variables, add a new environment variable, and then we want to add the S3 bucket that our code is going to be uploading to. So the S3 bucket that we just created is brand new. The code is pre-written, so it's not hard-coded. Instead, we need to set it as an environment variable, and then the code will retrieve that information from the environment variable. So the key will be S3_bucket in all capital letters, and then the value should be the name of your bucket, which for me is Data Lakes-Week 2-MW 2022. Then we'll go ahead and click Save. All right. So now what we need to do is go to the Permissions tab, and then I want to scroll down here, and for the role, let's go ahead and choose this link. And now this will open up in a new tab, and what I'm going to do is copy the ARN for this role. And the reason for that is that the code that we just uploaded is uploading to S3 and Amazon Elasticsearch. So I need to make sure that we can actually make that call. So giving the permissions to the Lambda function isn't enough by itself. We also then need to make sure that the S3 bucket policy will allow that call to be made. So I'm going to copy this ARN and paste it in a notepad that I have over on the side here. And then we're going to go back in our Lambda function console, and we're going to scroll up and type in S3 so that we can go modify that bucket access policy. Okay, so now we will select this bucket that we created, click on the Permissions tab, scroll down to the bucket policy and click Edit. And for here, you would paste in the provided JSON code that was in the instructions. And this is going to allow a principal to do any S3 action against a resource. So for the resource, you want to copy the bucket ARN from the top there, and then you can just paste that in just like this. And then the ARN for the principal that needs to be filled in is actually going to be the Lambda execution role. So I'm going to delete the brackets and the fill me in. And then this is what this policy will look like. So we are saying I want to allow all actions against S3, what S3 resource, this data lakes bucket specifically, and then for what principal, for the execution role of the Lambda function. So then I'll click Save Changes here. And now we can return to our OpenSearch service domain and see if our domain is done. All right, let's go ahead and click on our domain. And we can see that that status is loading. We will come back when this is done. All right, so we're back and we can see that we have an active domain. So what I want to do is click on the domain and then note how we now have a domain endpoint. So that's going to come important later. So what we want to do is click Actions for now. And what we need to do is edit the security of this so that way our Lambda function can actually write things to this domain to record those water temperatures. So I want to click on Edit Security Configuration. And then what I want to do is scroll down to this access policy and click on the JSON tab. And then I'm going to highlight this JSON function and delete it, and then paste in the JSON from the lab instructions. And then what I want to do is paste back in some important pieces. So I want to make sure that the ARN for this domain is pointing to my account. So I'm going to do that first. And then what I want to do is put back in my IP address. So I'm going to go ahead and do that. And then the last thing I need to do is paste in the role for that Lambda function. So I have that also in my text editor on a different screen. So I'll copy that and paste it over here. So now we have a JSON policy that is going to allow actions against this domain as long as it's coming from this IP address. And we also have another statement here that's going to allow actions against this domain as long as the principal is that Lambda function's execution role. So now we can go ahead, scroll down and click Save Changes. So now the permissions on this have been updated. So now the next thing we need to do is modify the Lambda function to add an environment variable that's going to point the code to this domain. So I'm going to go ahead and copy this domain endpoint and make a note of it in my tab over here. And then I'm going to navigate to the Lambda service, click on Lambda, click on my upload data function, click on the configuration tab, click on the environment variables tab on the left-hand side, click edit. I want to click add environment variable. And now I'm going to add one for ES domain URL. And then I want to paste in that domain URL that I had noted in the last step. Oops, pasted it in the wrong spot. Let me go ahead and fix that. Okay, so then we paste that there, and then I'm going to click Save. All right, so now what we need to do is create an API gateway that's going to forward requests to this Lambda function. So we have API gateway sending to Lambda, Lambda sending to S3, and OpenSearch service. So we need that API gateway piece next. So we're going to go ahead and open up the service API gateway. So we'll navigate to API gateway. And then I want to create a new API. And I'm going to select the REST API and click Build. And if you need to, you might also need to close some dialog boxes about creating your first API. I didn't have that come up, so I don't need to exit them. But if you get any dialogues, just go ahead and close out of those. So now what I want to do is give this API a name. I'm going to name it sensor data, and then I'm going to click Create API. Now I need to create my methods and my resources. So what I want to do next is click on Actions and then click Create Method. And then from this drop down, I will go ahead and select Post because we're going to be accepting posts from those sensors. So the sensors are going to be posting using an HTTP post to send that data. So now at this point, we need to set up some details for this post. For the integration type is going to be Lambda because the API gateway will be sending information to the Lambda function. And then under Lambda function, we need to select the correct one. So if you start typing upload data, we can select that there and then click save. Add permission to Lambda function. We're going to give API gateway permission to invoke the Lambda function. We're going to go ahead and say okay to that, say yes. And now that this post method execution has been created, we're in this method execution pane. I'm going to go ahead and click the test button here and then scroll down to the request body and paste in some data. So this is going to be mocking up, testing the data. So you can imagine this data coming from an outside sensor. We're going to just go ahead and paste it right in here so that we can test it directly from the API Gateway console. So I'll go ahead and click test. And now if we look over in these logs on the right-hand side, we can scroll down and we can see sending request to the Lambda function. And then we can see that we got a 200 status from that Lambda function and we successfully completed this execution. So this looks like it did work. So next what we need to do is check the OpenSearch service domain for this data. So what we need to do here is we want to query the domain. And in the instructions, it provides you an example of the pattern for the URL that you're going to enter into the browser. So now that we have tested this through API Gateway, what we need to do now is check the OpenSearch service for data. So in the instructions, it gives you a template for how to create the URL to actually query your domain. So what I want to do is show you what it looks like after I did my query here. So I'm going to bring this over to this screen and you can see I have my domain. So the search water temp domain and the domain /lambda s3 index /lambda type /_search question pretty. And then this is what came back once I made that request. So we can see that I had a sensor ID and the timestamp and the temperature, which if we come back here, we can see that that does match what we entered in to our request body, testing it through API Gateway. So in the real world, your data probably wouldn't originate from API Gateway. It would come from a fleet of sensors and devices. But again, we've generated things through API Gateway as if it was coming from outside. And by creating the OpenSearch service domain, you also now have access to Kibana, where you can then go and further explore, view, and analyze the data that was loaded. So from here, we need to go ahead and clean everything up. And to do that, you would want to navigate to IAM, click IAM, and then we want to delete the role first. So we can click here on Data Lake Week 2 and click delete. And then we can delete the role. Delete. And then next we need to delete the OpenSearch service domain. So we will go ahead and navigate to OpenSearch, select OpenSearch, and then we want to go to all domains, select the domain and delete it, and then type in the name water temp domain to delete it. Water temp domain, and then click delete. And then we want to navigate to S3. And for S3, we want to delete our bucket here. So I'm going to go ahead and click this, click delete. Oh, we need to empty the bucket first. Let's go ahead and do that. So we can see this JSON that was from the Lambda function. We're going to go ahead and delete this. And you would type permanently delete and then click delete objects. Now we can come back to the source, go back to buckets, and then we can click this, click delete. We want to delete this bucket, so I'm just going to copy and paste the name into the delete field. And then we need to delete the Lambda function. So I'll navigate to Lambda, select upload data, click actions, click delete, and then type delete to confirm, click delete, exit this. And now finally, API Gateway. We can delete that one as well. Click API Gateway. Select the sensor data API, select actions, select delete, click delete. And that is it. We are totally cleaned up from this lab. All right, thank you. See you next time.
Welcome to week 3. It makes me happy that you have learned about the AWS services that are mostly used for data lakes. Now that you know the basic concepts and the services used for data lake operations, let's dive deeper into the services that are mainly used for data ingestion and cataloging. Each data lake is unique, and the need for a data lake varies from scenario to scenario. So it is essential to understand the differences between ingestion mechanisms in order to choose the right tool for the job. During this week, you will learn more about data structure, when is the right time to process data, learn more about Amazon Kinesis data streams, Kinesis Firehose, Kinesis Analytics, and other data ingestion services such as AWS Snow Family and AWS Transfer Family. I will also cover a fundamental aspect of data lakes, data cataloging and metastore. You will see a demo of how using AWS Glue crawlers can help you on taking your data cataloging to the next level. In the architecture review video at the end of the week, I will also review the specifics of data ingestion mechanism using data lakes architecture diagrams. So let's get started. As you know, you don't want your data lake to become a data swamp, so I don't need to say again that you would like to have a minimum level of data organization and categorization in your data lake. To better understand what I mean by organization and categorization, let me compare with a library. Imagine a library with thousands of books, where those books are all piled up together without any sort of categorization. As you may expect, it would be very hard to find books if they are organized like that. The most optimal way for people to find books in libraries is to organize them under main topics that are both easy to memorize and reduces the number of titles to search when you're looking for something. That's why we have categories such as arts, comic books, romance, history, computer science, etc. For centuries, libraries are organized that way for a reason. And the reason is that it matches the access pattern used when someone is looking for a title. That being said, if you're looking for a book containing food recipes, it makes more sense to go for the cookbook section instead of the science fiction. Now let's take the number of pages as another example of cataloging books. Imagine that you have library shelves filled up with books sorted by number of pages, in a way that cookbooks and computer science books could be close to each other if they have approximate number of pages. That way of cataloging books would make it easy if someone is looking for books that can be quickly read, but it is not very practical in reality because most of us use access patterns of finding books by subject or by the combination of title and author. As you see, one method of categorizing data is not necessarily better than any other, and it is all about finding the most appropriate method of categorizing according to the access pattern. The very same principle applies to your data lake. As you have people looking for books in libraries, in your data lake, you will have computer systems or AWS services getting data to process. So you should consider classifying the data according to the access pattern needed by those. For your data lake, you may have auto-generated data, such as data generated from IoT devices or server logs. Those often come via streaming and are typically unstructured. Suitable to ingest with Amazon Kinesis, store in Amazon S3, catalog with AWS Glue, process with Lambda, and query with Amazon Athena. You may also have operational data, such as inventory and sales, expense reports, and other inputs. Those likely come in batches and are usually consumed by people who want to visualize graphs and have access to statistics. This data may be suitable for being ingested with API Gateway, stored in S3, cataloged with Glue, transported to Amazon Elasticsearch Service, and visualized with Kibana. In addition to that, you may want to have human-generated data, such as social media feeds, contact forms, call center audio, emails, etc. For these, you may think about access patterns needed by data analysis services. You could ingest that data with S3 SFTP or AppFlow, store it in S3, catalog with Glue, and use a service like Amazon Comprehend, which is a natural language processing service that uses machine learning to find insights in texts, such as sentimental analysis. For each one of those scenarios, you may want to use a specific ingestion and processing layer that is the right tool for the job. And depending on which processing tool you are going to use, you may want to design your data to match the access pattern needed by the processing layer. That includes shaping the data to a specific file format, compressing, splitting, aggregating, or any other data transformation. Rest assured that we will cover more about data prep later in this course. Notice that I mentioned storing in S3 and catalog with Glue in all previous cases, and that is because those services are specifically designed to work with storage and cataloging in a data-agnostic way, keeping your data organized and preventing the data swamp. An important concept to understand is the difference between structured and unstructured data. Let me explain the difference. Structured data is data that is easy for a computer systems to consume in its format without further modification. You have highly structured data if you think about a relational database table with its schema, primary keys and foreign keys, and associated data relationships, where the database engine may even reject data that does not fit on that rigid structure. While structured data processing was the most popular option in the world of analytics for a long time, with the rise of Internet of Things and other real-time data sources, the benefits of transforming real-world data into insights as quickly as possible brought business advantages never imagined before, and having the capability of dealing with unstructured data allow you to reach insights faster. For example, if you have an IoT device that captures temperature and sends that as a number to a system, that data has high probability of being structured or at least semi-structured. But if you have IoT devices that collect audio or video files and send those files for further processing, we are talking about unstructured data. I've seen people confusing this and thinking that unstructured data is structured because it uses the same file format across the dataset. As you see, it is not about the file format, but the data content. Data formats are just the format that was chosen to represent the data. And let me use CSV files as an example. CSV files are plain text files that contains a list of data. Although it is a friendly format to provide structured data, the file format itself cannot guarantee that data inside a CSV file is properly strongly structured. I'm saying that because you may have lines in a file containing data that has more or fewer fields, or sometimes you have a comma that has not been properly escaped, leading to think that it was a delimiter when it was not. Some data processing services like Amazon EMR or AWS Glue are ideal for working with unstructured data. If you see those as the first processing layer on data lake architectures, it is very likely that they are being used to transform unstructured data into structured data, which may be needed by further processing layers that work with structured data only to reach high performances at lower costs. Another important aspect to consider is when you are doing the data processing, because you may want to process before, after, or before and after storing the data. You may be familiar with the concept of ETL, or extract, transform, and load. This concept is not new and has been around for decades. For data lakes, you may want to practice what we call ELT, which is extract, load, and then transform. A simple order change in the letters L and T. Let me tell you some applicable scenarios on ETL versus ELT, or even ETLT. Let's say you are working in a company that does interplanetary expeditions, where you have devices on other planets sending their findings. This type of data is absolutely rare, and no matter what you are going to do with that data, you want to store the data in its raw format to avoid losing anything. In this case, you would like to store immediately without any kind of pre-processing. In this case, you would like to perform the classic ELT, extract and load, and then in the future, do some eventual transformation. Think that if you transform before loading, you may risk losing something. Now let's come back to Earth, and imagine you are working with a medical system that needs to meet compliance standards where you cannot store PII, or personally identifiable information. If you receive MRI or X-ray images from medical hardware, you can remove the PII during the data ingestion before storing into a storage service like Amazon S3. Once data lands in S3, you can run another processing layer that will convert the images into a friendly file format that is needed for the data statistics components or any other processing layer. You may be asking why not doing both PII cleaning and image conversion at the same time on the first wave of data processing when data was being ingested. There may be multiple reasons for the need of doing that way. One is that the two data processes may require different sets of services, making it natural to split in two because you would need two different types of services to process anyway. Another reason could be that the second processing may need information that is not available at the moment data has been ingested, hence the need to store first and then post-process. This is a scenario where you would like to do what we call ETLT, which is extract, do a little transformation such as the PII removal, load, and then do a major transformation. I personally like to call it and represent the more complex transformation with an uppercase T, but those are just letters to illustrate a flow, so don't worry too much about it. The important thing here is to understand the components. Do you see how everything depends on the scenario? That's why using the right tool for the job and knowing when to process data is important when we are talking about data lakes ingestion and processing. One of the core capabilities of a data lake architecture is the ability to quickly and easily ingest multiple types of data, either in terms of structure and data flow, such as real-time streaming or bulk data assets from external platforms. You may already know the difference between batch and streaming data. In a nutshell, we usually think about streaming when we have high volume of small bits of data that needs to be processed or stored while data is arriving. But since ingesting a high volume of data at a lower latency may come with a cost, you can benefit from ingesting your data in batches if a longer time to insight can be afforded. AWS offers a whole suite of data ingestion services, and I strongly suggest you visit the course notes to get more information about them. But one thing is for sure, it is impossible to talk about data streaming on AWS without talking about Amazon Kinesis, because Kinesis is the most popular data streaming service in the AWS cloud. Amazon Kinesis is actually a family of data streaming services divided into Amazon Kinesis Data Streams, Kinesis Analytics, Kinesis Firehose, and Kinesis Video Streams. Let's talk about Kinesis Pure Form, which is Kinesis Data Streams. Then I will talk about Firehose and Analytics. This diagram shows you a Kinesis data streams with the data producers on the left side and data consumers on the right side. In this example, I am illustrating IoT sensors, web server logs, and clickstream data on the producer side, and an EC2 instance and Lambda functions as consumers. The EC2 instances are doing some processing, and the Lambda functions are just storing data into S3. There are three important things I want to talk about this diagram. First, Kinesis is data agnostic. Second, data retention period and data consumption replay. And third, pool-based mechanism. Understanding those concepts will make you powerful enough to explain what Kinesis is to all your family, friends, and coworkers. Isn't that nice? The first one is the fact that Kinesis is data agnostic. You can see that by the different data producers sending data to the same Kinesis data stream. You can send JSON or XML, structured or unstructured data. If you send it properly by using the Kinesis SDK, Kinesis will store it. You may want to create one Kinesis data stream per data type, or concentrate data in the same Kinesis data streams like I am doing in this diagram. The way you design your architecture is up to you. The second aspect of the diagram is that data remains in the Kinesis data streams, regardless if it has been consumed or not. Data stays there until it expires according to what we call a data retention period. That data retention period is 24 hours by default, but you can extend that by doing service API calls, which would also increase the hourly cost of the Kinesis data stream. Keeping the data in Kinesis is valuable because multiple consumers can consume the same data at the same time. In addition to that, it allows replaying the data consumption in case of data consumer failures. Let me explain. Imagine you have an application consuming the data. If that application crashes, you can run it again and set a past start position. If that past start position is within the data retention window configured in the Kinesis stream, your application can consume data added to the stream while it was offline. The third thing I want you to notice in the diagram is the direction of the arrows on the data consumer side, on the right side of the diagram. In some diagrams, you may see arrows from left to right because that's the overall direction of the data flow. But I think it is more technically accurate when you point arrows from consumers to Kinesis and not from Kinesis to consumers. And here is why. Kinesis does not work as a push-based delivery mechanism. If a consumer wants to consume Kinesis data, it must initiate a connection using the Kinesis client library, available for most popular programming languages. That code can run from on-premises, from within an EC2 instance, from your laptop, or from within a Lambda function. People usually write Kinesis consumers for two main reasons: getting the data and placing it somewhere, such as a storage service, and two, performing some real-time analysis of data that is passing on the stream. Speaking about the first one, what would be the most popular data storage service in AWS? Let me give you a couple of seconds. I would agree with you if you said Amazon S3. AWS realized that most customers were writing Kinesis consumers just to get data and move to S3 with minimal modification, such as compression or encryption. To make your life easier, we created Amazon Kinesis Firehose. Firehose is part of Amazon Kinesis family and helps you have data available for multiple destinations. With a few mouse clicks in the AWS Management Console, you can have Kinesis Firehose configured to get data from a Kinesis data stream and put into a destination like Amazon S3, Redshift, Amazon Elasticsearch, HTTP endpoints, or third-party service providers such as Datadog, Splunk, and others. Now let's talk about real-time analysis of data that is passing by the stream. If you want to control the code that is analyzing your data, the easiest and most popular way is via AWS Lambda functions. Since both are AWS managed services, there is some polling made behind the curtains that invoke the Lambda function when there is new data in the stream. So, the Lambda function that receives the data without having to concern with the polling part, looking a lot like a push-based architecture. Interacting with Kinesis via Lambda is easier than hosting code on EC2, but still requires you to write the code that will run in the Lambda function. Although there is some sample code in the AWS documentation, you may want to choose an even more convenient way of analyzing that streaming data. If you want to go fully serverless without writing that code, you can rely on Kinesis Analytics, a powerful real-time processing service with no servers to manage and, as usual, paying only for what you use. Kinesis Analytics allow you to write SQL queries to process data in real time, providing an easy way to query streaming data without having to learn new frameworks or languages. You can also write Apache Flink code for more sophisticated analysis. Flink is an open source framework and part of the Apache Foundation. Kinesis Analytics has two main concepts that are easy to understand: in-application streams and data pumps. Those concepts provide you the necessary abstraction to handle data that is passing through a data stream like water passing through a pipe. The additional reading of this week contains more information about those in-application streams and data pumps. The Kinesis Analytics documentation gives you detailed examples with sample queries ready to copy and paste to create both the in-application stream and data pumps. I strongly suggest you giving a try. As a recap, this diagram shows where you could use Kinesis Analytics and Kinesis Firehose to help you better understanding the scope of each service. Last but not least, you can also use Kinesis to ingest video and build video analytics applications. Kinesis Video Streams makes it easy to stream video from connected devices to AWS. You can use Kinesis Video to make an application that would interact with a camera-enabled doorbell from your mobile phone, for example. And that's it. I hope you enjoyed learning a little bit more about the AWS Kinesis family in this video. Depending on the use case, you may not have the need to ingest data via streaming. A typical use case for using batch data ingestion is when data has already been produced and is sitting somewhere, such as on-premises data centers or external hard drives. You may also want to use batch data ingestion if you're producing large amounts of data and the time required to produce insights is not time sensitive. For example, ingesting data periodically and running reports once in a while. There are many AWS services and services from AWS partners that can be used towards ingesting your data in batches. In this video, I'm going to talk about AWS Transfer Family. AWS Transfer Family is a serverless AWS service that gives you a file transfer endpoint in AWS without the need of running any server infrastructure. Let me show you how it works in a demo. In this demo, I am going to create an S3 bucket in my AWS account and an SSH key pair on my laptop, with a private key and a public key. Then, I will go to the AWS Transfer Family Management Console and create a publicly accessible SFTP server configured to allow file transfer over SSH, also called SCP. Then next, I am going to create an SFTP user called ref, associate that user with my public key, and use an IAM role to grant permissions to the S3 bucket I created. Once everything is configured on AWS, I will open my FTP client and test everything out. I'm going to be using FileZilla for the FTP client. So let's go. So the first step is opening my terminal and doing the command AWS S3 MB. Then I give an S3 endpoint for the AWS command line, S3 / SFTP test ref. MB as in make bucket. So this is an AWS CLI command line interface command that will create a bucket for me. If we go to the AWS Management Console and click in S3, we will see that the bucket had been created in my account. Now let's go back to my terminal and I will be going to the folder /tmp, a temporary folder in my computer. I'm going to create a directory called FTP, and inside this directory, I'm going to create the SSH key pair, the public key and the private key. And I can do that with this command, ssh keygen -trsa. Here I specify what will be the path of the file that I will want to create, ID RSA, and in this case, I'm going to put no passphrase. So the public key and the private key had been generated on /tmp/ftp, and the private key is called ID RSA, and the public key is called idrsa.pub. If you see the content of those two files, the ID RSA contains the OpenSSH private key, and the idrsa.pub contains the OpenSSH public key. This is the key that we'll be interested on copy and pasting on AWS Transfer Family when we create the user Raphael. So now let's go to my Google Chrome again and go to AWS Transfer Family. What I would like to do is to click here in Create Server. And here I can choose what are the protocols that I want to enable for my AWS Transfer Family server. It says server, but AWS will be managing that server for you under the hood. So that's why we end up saying that this is a serverless service, even though there is a server running behind the scenes. In this case, I will choose SFTP, which is the file transfer over secure shell. Then I'm going to click in next. Here is if I want to choose a custom identity provider. In this case, I'm going to have the AWS Transfer Family to manage the users and permissions for me, but I could use API Gateway with a customer identity provider. Here is what I want my server to be publicly accessible, or if I want my SFTP endpoints to be only accessible from within an AWS VPC, which is a virtual private cloud. In this case, I want it publicly accessible, and I will be relying on the key authentication. Here is where I could provide a custom host name. So if you already have an FTP server in your organization and you want to use that custom domain name, you can use Route 53, which is AWS domain service, to use the custom domain of your preference. So if you have, for example, ftp.yourcompany.com, you can use a Route 53 DNS here. In this case, I'm going to use none, and I'm going to use the endpoint that is provided by AWS Transfer Family. I'm going to hit next. I'm going to pass over those, keeping everything on the defaults. And here, it uses a role for logging. So remember that AWS Transfer Family can log everything to CloudWatch logs, such as the connection that had been made, connections that are closed, put object, get object activity, or put file and get file on the FTP nomenclature. And it writes that on CloudWatch logs using a role, an IAM role. You can choose an existing one, but in this case, I'm going to ask the service to create one for myself. Tags are important to keep your infrastructure organized. So let me put some tags here, such as creator, cost-centered, and other things that could help me doing billing reports based by tags. I'm going to hit next. Then this screen here gives me the option of reviewing everything that I've chosen so far and creating. So the server creation can take a couple of minutes. Meanwhile, we can add users to that server. So we click here on the server ID, we scroll down to users, and we hit add user. I'm going to create a user called ref, and here I must choose a role that I want the AWS Transfer Family to assume on behalf of this user when an FTP connection from this user comes. I have already previously created the IAM role that will allow that, which is called allow SFTP user to specific S3 bucket. In AWS, we'll talk a lot about the least privilege principle, which is only allowing users what the permission they need to do the specific action they want. So after I create this user, while the server is being created, I am going to the IAM console to show you how is the anatomy of this role. So here I have the role previously created, I just choose the role. And here I choose what will be the SFTP home directory for this user, which is the bucket that I had created. Now on the SSH public key, I can go back to my terminal and copy the public key and paste the public key here. Which means that this public key has this private key as the corresponding key. So whenever we need to authenticate to that SFTP server, this is the private key that we will be using because it corresponds to the public key that we are informing to the service. Then we hit add. And now I have the SFTP server being created. It is still starting. And this SFTP server already has a user associated to it. Now let's go to IAM. So as you can see how that role is created. If you go to IAM and click here in roles, you're going to see that I have a role called allow SFTP user to specific S3 bucket, which is the role I chose for the user ref. And every IAM role needs to have a trust relationship, which means who can assume that role, and the permissions, which are the powers of that role. In this case, the trust relationship of this role is transfer.amazonaws.com, which is the name of AWS Transfer Family in terms of API to IAM. The permissions are allowing that user only to a specific bucket. I don't want to allow that role access to any bucket because we want to reinforce the least privilege principle here. So I created an inline policy and added that inline policy to this role. If we expand here the JSON document for that role, we are seeing that this specific role has a permission that will allow this role to list bucket and get bucket location only for that specific bucket. And also, only for everything inside that specific bucket, I want to allow put object, get object, delete object version, delete object, and get object version. This is reinforcing the least privilege principle, because now the user ref on AWS Transfer Family will only have those permission sets in the specific bucket. Now let me go back to my AWS Transfer Family and see if my server had already been created. It says that the server is online, so now it may be time to open my FileZilla and test everything. If you click here, you also have the option to stop and start the server. And if you click here in View Logs, you are redirected to the AWS Management Console of CloudWatch Logs, where you can see which users connected, which files had been uploaded and downloaded via FTP. Before opening FileZilla, we would like to copy the endpoint where we should point our FileZilla to. Now let's open my FileZilla, and I'm going to click here and create a new connection pointing to that specific host name. I'm going to be using a key file, which I already have populated here in my FileZilla, but /tmp/ftp/id/rsa is the very same file as this one. So once I click in connect, I click in OK to accept the key negotiation handshake. It is using the username ref authenticated by that key. And you can see that on the remote directory, I have my home directory, which is sftp test ref. Now, if I go back to my terminal, I can create a file. This is a text file. I save the file. Now, if I go back to my FileZilla, the file will be there, file.txt on /tmp/ftp, which is the file that we just created. And if I drag and drop this file from the local directory to the remote directory, what I have happening under the hood is an FTP put to a server that I don't need to manage, and that server is assuming a role in AWS and doing a put object operation to Amazon S3 on behalf of that role. If we go back to the AWS Management Console and go in S3 and open our bucket, we are going to see that file.txt is inside our bucket sftp test ref. This file is not public by default because the bucket is not public. Private buckets is what you would like to have for your data lake assets. See how simple it is? There are some other features you can use, such as custom domain names, custom identity providers for user federation, and much more. AWS Transfer Family logs all the activity in CloudWatch Logs for further auditing if needed. Depending on where the data is, internet connectivity may not be reliable, or the uplink may be used for something else, such as the production workload in a data center, not allowing you to copy large amounts of data using the internet. Amazon has a pretty good expertise on sending and receiving packages from customers, and sometimes having Amazon sending you a physical device for you to copy your data may be faster than waiting for uploads using the internet links. If that is the case, AWS Snow Family to the rescue. AWS Snow Family is a family of services designated for offline data transfer. Actually, since we are recording these videos from our homes, Morgan and I are using the Snowcone devices to upload our video footages to Amazon S3. That's why I have one here with me. This is a Snowcone device. Its capacity is 8 terabytes and arrived to me the next business day after requesting it via the AWS Management Console. How long would it take to copy 8 terabytes of data to Amazon AWS? Well, according to my calculations, with my 40 megabits per second upload speed, it would take around 18 days non-stop to complete this data transfer, which could fail in the middle or have the risk of being throttled by my internet service provider, taking it longer or even being unfeasible. The Snowcone is a ruggedized, tamper-proof, dust-proof, and water-resistant device. It weighs 2.1 kilograms and is powered with a USB-C power adapter. It comes equipped with two 10 gigabits per second Ethernet ports to plug in your local network. You can download a provided software called AWS Ops Hub, which contains a graphical user interface that assists you with unlocking the device and copying your data to it in a secure way, using encryption keys you manage through the AWS Key Management Service, or AWS KMS, providing encryption both in transit and at rest. This device also comes with some onboard computing power. This specific one I have in my hands has computing resources to collect and process data with AWS services at the edge. It locally runs specific Amazon EC2 instances with 2 CPUs and 4 GB of memory, being very handy to make simple data transformations or perform some processing before adding data into S3, or the final destination of the data. The device is also equipped with an e-ink display that gets the information regarding the return label needed for shipping it back to AWS. If you need more capacity, you can order a Snowball device, which is another member from the AWS Snow family. They share the same principle as snow cones, but they are bigger, heavier, and more dense in capacity, providing more than 50 terabytes per device. If you need more capacity, you can always order multiple Snowball devices and cluster them together to combine their storage capacity. Okay, if you want to do this with petabytes, you can contact an AWS sales representative and you will basically have a data center on wheels sent to you. This is called AWS Snowmobile, an exabyte scale data transfer service used to move extremely large amounts of data to AWS. You can transfer up to 100 petabytes per Snowmobile. As you can imagine, it is not the type of data transfer mechanism we would use every other day. That's it. Now that you know more about data ingestion to your data lake, we will talk about data cataloging. I am happy that you learned more about data ingestion and some AWS services used in the field. Don't forget to explore other data ingestion services as well. In this video, we are going to talk about a crucial aspect of data lakes, what to store in a data catalog, and what are the AWS services used towards it. If you want to have a mature data architecture, you should keep track of all the assets as they were loaded into the data lake, and then track all of the new data and versions that were created by data transformation, processing, and analytics. Since Amazon S3 is commonly used for storage, we usually make use of multiple AWS services for the data catalog, which should be designed to provide a single source of truth about the data that sits in the data lake. There are two general forms of cataloging data: the comprehensive data catalog and the H catalog, also known as Hive Store Catalog. The difference is, while a comprehensive catalog contains information about all ingested data, the H catalog contains information about data assets that have been transformed and ready to be used with data processing services, such as Amazon Athena, Amazon EMR, and others. Think about the comprehensive catalog as being a general database containing everything, and the H catalog the tool used by processing services to extract insights. It doesn't need to be one or another. Most data lakes contains both H catalog and a comprehensive catalog. They complement each other because while comprehensive data catalogs are used to search for assets in the data lake, the H catalog can be used to discover and query the data that was found by the comprehensive catalog. The diagram you see represents a high-level view of a comprehensive data catalog created by using standard AWS services. In this case, Lambda triggers are used in response to putting objects in S3. Those lambdas populate DynamoDB tables containing object names and extra information about them. Lambda is also being used to index information in Amazon Elasticsearch Service, which can be further used to search for specific assets. Using DynamoDB for a document database and Amazon Elasticsearch Service for a full-text search engine ties pretty well with the mindset of using the right tool for the job. Now let's talk about the H catalog. It is common to have the H catalog made of AWS Glue databases and tables with the ability of using a Glue crawler to create them. Those are the tables you query with Amazon Athena and other processing tools that uses a standard Hive Metastore catalog, such as Hadoop. AWS Glue and Amazon Athena are best friends, which means that the table you create on Glue are naturally taken as table you can query with Amazon Athena. So, when you want to use Athena for querying data, the query is actually performed against a table in Glue. We usually call them Athena tables for simplicity. This is a command used to create a table in AWS Glue. In this example, the table maps to CSV files in S3. These CSV files contain information about taxi rides in New York City. There are three important components here. First, the location. Second, the serializer and deserializer, also known by CERD. And third, the table schema. Once you have the where, how, and what properly configured, you have a working table in the Glue H catalog, which you can perform SQL queries with Amazon Athena. What I mean by where is where the data can be found when a query is made against the table. In this case, it is represented by an S3 prefix in the location part of the command. Also, notice that when we create the table, we specify external table. That's because data is stored primarily in S3, not in Glue. What I mean by how is the instructions that indicates how the query executioner will parse the S3 files, mapping the table columns to the information in the file. Those are known by CERDs, which is a term for serializer-deserializer. If the files are in the CSV format, you should use a CSV CERD, same with JSON, Parquet, and other formats. If you use a JSON CERD to query CSV data, it will be like trying to watch a DVD movie by trying to insert the disk in a VHS systems. You will have errors. What I mean by what here is the table schema, which in this case is similar to a table schema in SQL, made by columns and data types. In the sample table, we have columns like trip distance, fare amount, trip amount, and other values contained in the CSV files in S3. The good news is that Glue has a feature called Glue Crawler. Crawlers can create tables automatically for you. The crawlers are handy, especially when you have custom data formats, because it reverse engineers what you have in the files and automatically infer the schema for you. That's it. I hope you learned more about data cataloging in this video. I strongly suggest reading the course notes if you're looking for more information about data cataloging. We put good readings for you in there. Alright, let me quickly show you how to use Glue crawlers to have the crawler going into your dataset and inferring the schema. We are going to start with the registry of open data on AWS, which you can find on registry.opendata.aws. This page is part of what we call the AWS datasets, and Morgan will talk about that in a dedicated video on the week 4. For now, the most interesting relevant part for us is the New York City Taxi and Limousine Commission TLC trip record data. If you click here in details, you can see that AWS maintains this dataset for customers who wants to do analytics with data collected by taxis and limousines in the New York City. This is all stored in a bucket called NYC TLC, and that's why I am going to my terminal and I am going to list the contents of this bucket. It's a public bucket, so AWS S3LS, S3 endpoint, New York City TLC. And you will see that this public bucket has miscellaneous, and trip data. So let's go on AWS S3LS, NYC TLC, trip data. You will see that it is a bucket containing lots of CSV files, as you can tell, right? And you can tell that those CSV files are separated by year and month, but they are all in the same root directory of the bucket. So if we run a crawler against this bucket, it would scan every single file in it. So to avoid that, and to make the demo faster, I will create a crawler, and I want the specific crawler to crawl only one specific file, which is this exact one, 2018/06.csv. What I'm going to do is create a bucket in my account. Called TLC ref demo. So I made this bucket in my account, and now I am going to copy only one of those files into my bucket. And I can do that with AWS S3CP, New York City TLC, trip trip data, yellow trip data 2018-06.csv, which is this file here, right? Yellow trip data 2018-06.csv. And now I want to copy this file from this bucket to my bucket, TLC ref demo. Now notice something very interesting. When you do AWS S3 CP using one S3 bucket as source and another S3 bucket as destination, it goes from bucket to bucket. So that transfer has this speed because it doesn't pass through my computer. It is going from one AWS public bucket to a bucket that belonged to my account, which is the bucket that I just created. Okay. So transfer is completed. Now I am going to do AWS S3 to my bucket. And the file is there. You can also see the file on the S3 Management Console. So if you go to S3, there is a bucket called TLC ref demo. And there is only one file inside that bucket, which is the file that I just copied. Now I want you to notice the size of this file, 700 megabytes, 733, right? 733 megabytes. And let's also sneak and peek the structure of this file. I'm going to be doing, I downloaded the file to my computer as well, to the folder /tmp/tlc. And I'm going to head this file. Head is a Linux command that only displays the top lines of a specific file. This is how the file is structured, and these are the first lines of the file. It's a CSV file, so you can see that we have values separated by comma. All right. And here is the names of each one of these data. Now, remember when I said that structured data is not about the file formats, but about the file content? Let's say that in one of these timestamps here, you have a column by mistake, right? That would make this file an unstructured file, because you are having something that could confuse any parser that would load this file thinking that it is a delimiter, and the delimiter is the comma, right? So file format is file format, data structure is data structure. One thing is not necessarily related to each other, and there are some file types that are friendly to structured formats. So this file is a structure because it had been already cleaned by AWS datasets. And here we have vendor ID, so this is vendor ID 1, TPEP, PCOP. I need to see the documentation for this dataset to see what TPEP means. So we have passenger count, trip distance. So 1, 2, 3, 4, 5. The fifth field is the passenger count. So 1, 2, 3, 4, 5. I don't know, maybe what here, 1 passenger, right? So if you want to see the number of lines in this file, we can run with the wc-l command to count the number of lines, and we see that this file has 8 million lines, right? 8.7 million lines. So it's a long file. It's not compressed, so it occupies 734 megabytes, right? Now let's go back to Glue and let's create a crawler that will get this file, infer that specific schema, and create a Glue table for us. Let's go to Services, AWS Glue, and then here on the sidebar, I would like to locate the crawlers and click in the button Add Crawler. Here is the crawler name. I'm going to call this crawler name TLC crawler. And then I should choose a data store for my crawler. And the data store is going to be S3 TLC ref demo, which is the bucket that I just created. If I wanted to use that original bucket, I would need to put /trip data/ and the specific file. But if you just specify the bucket, the crawler will crawl, the crawler will locate all the files and infer the schema for them. So this is my path. Next, I can run the same crawler crawling multiple data stores, which is not the case. And here I can specify the IAM role which the glue crawler will assume to have get object access to that S3 bucket. I have the option of creating a new role here or using a role that already exists in my account. So create an IAM role. Let me call this crawler role. Next. Here is the frequency I want to run that specific crawler. For this case, I'm going to run on demand, which means that I will manually invoke that crawler. And here I can add a database. This database is a database that will be added to the Glue H catalog. I'm going to call that database TLC. And here is if I want to add any prefix to the tables that will be created to my Glue H catalog as the crawler output. I will leave this as empty. I will hit next. Here I have an option of reviewing how the crawler will be. It will use this IAM role. It will run on demand. The output of the crawler will creating a database called TLC in my Glue H catalog and finish. Now the crawler is being created and the crawler needs to be run manually. So I need to click here and click in Run Crawler. Now it is attempting to run the crawler and the crawler is running. What this crawler will do is go into my S3 bucket, the S3 bucket that I specified. It will do a get object. It will get that 700 megabytes file. It will get the first line. It will see vendor ID, TPAP, PCOP, and date time, and all the file structure that I have inside that CSV file. And it will create a table in the Glue H catalog. Using CSV as a CERD, it will see that the content separator is comma, and it will create a table with those columns. So when we go back to the crawler, you can see that the crawler added one table in our Glue data catalog. If we click in the crawler, we can see the preferences of the crawler. And if we go here on the Glue catalog databases, you will see that there is one database created. And if you click here in tables in that database, you can see what are the tables that are in this database. And here is the most interesting thing. Here is the output of what the crawler did. The crawler scanned the file and inferred the schema for me with the specific data types corresponding to each one of the specific fields inside the CSV file, right? That CSV file, if I open that CSV file with VI in my computer, you can see it is a long file. As we saw with WC, it has 7 million lines, right? So it is endless. It basically has 7 million things here. What the crawler did was opening the first couple of thousands of lines to infer that specific schema, okay? So here is the table, and here are the column names and the data types of this table. Here is the CERD that was used, which is the CSV CERD, a very simple CERD. But the main benefit of this crawler is if you have a custom file, if you have an access log, if you have a file that is not CSV, if you have a JSON file, if you have a columnar data type file, okay? So here is the table, and this table is a table I can query with Amazon Athena. You can also edit the schema by removing some fields if you want to remove that from the Athena table. The file on S3 remains untouched, but the table in the Glue Metastore will not have that specific column. Or you can also add some columns. The crawler is also responsible for scanning the files from time to time and altering the table schema if the file schema changes. When you configure the crawler, you can ask the crawler to let you know what to do. If it wants to notify you, or if you want the crawler to change the table schema for you automatically. And that's it. This is how you create a glue crawler and point the crawler to your dataset and have the crawler inferring the schema for you. Now, let's take a diagram to illustrate some things I talked about during this week. In this video, we are going to analyze the specifics of data ingestion using an architectural diagram. One of the most common data analysis we do with big data is log analytics. Log analysis allows you to analyze logs from websites, mobile devices, servers, sensors, and more, enabling a wide variety of applications such as digital marketing, application monitoring, fraud detection, ad tech, gaming, IoT, and much more. Here is a diagram representing a data ingestion solution built for doing analytics with web server logs. This specific solution is reliable, cost-effective, scales automatically, and requires almost no IT administration because, as you can see, we are only using AWS managed services such as Amazon S3, the services from the Amazon Kinesis family, and Amazon Elasticsearch service, which gives you a managed Elasticsearch domain with plugins like Kibana already installed and ready to use. In this case, we have data being produced by the Amazon Kinesis agents running on EC2 instances configured to send the contents in the log files straight out to Kinesis Firehose. That Kinesis Firehose has Amazon S3 as destination for storing the raw data, but you can see it also has a Kinesis Analytics application attached to it. In this case, the Kinesis Analytics is using a SQL query to perform an aggregation on data points with larger granularities, such as, for example, summarizing data points per minute, which will be convenient for the Elasticsearch to find things faster and also reduces the space occupied in the Elasticsearch cluster. Remember the video about using the right tool for the job and when to process data? Here we are doing ELT, because we are extracting the data, loading in S3 mostly as a backup, then we are transforming with Kinesis Analytics for further usage. For budget purposes, you can configure bucket lifecycle policies in that S3 bucket, making older contents to be automatically transitioned to S3 Glacier, and that's a pretty common practice among AWS customers. Now, from Kinesis Analytics to Elasticsearch. The easiest way to hand data from Kinesis Analytics to Elasticsearch is through Kinesis Firehose, and that's why we are connecting a Kinesis Firehose as the output of the Kinesis Analytics. When data is in Amazon Elasticsearch, users can log with Kibana to visualize data in form of charts. Those charts can be separated into units like number of HTTP 404 errors per minute or a sum of unique visitors towards a specific URLs, enabling extracting insights from the data produced by the server logs. You will learn next week about the power and the value proposition of using the right and proper data visualization tool. I hope this video was useful for you to better grasp how data ingestion and processing services can be used combined towards a solution. I chose this architectural diagram on a purpose to show you how you can have multiple Kinesis services chained to each other. As usual, remember that it is all about using the right tool for the job.
Hi, welcome to week 4 of the course. You're almost to the end, and we're happy you've made it along with us this far. This week, we will continue the data lakes journey by diving deeper into the data processing and analysis aspect of your data lake, by further exploring the service AWS Glue and Amazon Athena. Then we will cover the topic of data visualization and run through some examples using the service Amazon QuickSight. As always, please remember to read the course notes where we link to further documentation for you to access more details and use the course discussion forums to ask any questions that you may have. Ingesting raw data into a data lake is one thing, but actually making it useful is a totally different task that actually will account for probably 80% of the work. Data gets ingested in its raw format, and as you've learned, that data may or may not be formatted correctly for your use case. This is where data prep comes in. Prepping your data to be used by tools and services for analytics is a big job, and you'll likely spend a majority of your time writing scripts and devising solutions for making the data that you've already collected ready to be analyzed. It's even common to process the same data multiple times. You could use a dataset to generate reports for one use case, but then use that same dataset to train a machine learning model in a totally different use case. It's unlikely that these two use cases would require the data to be in the same format, which means processing the same data multiple times to fit each use case. A data lake can be seen as a central repository for data. And because of this, you cannot assume that you will be the only one using that data over time. Remember the idea of future-proofing? Well, it applies here as well. Remember that even though you may not have a use case for your data yet, you will in the future be able to draw insights from it. Better yet, you might think that you're the only one using your data now, but others might find use for it in the future. Therefore, leaving data in its raw format is a great idea, so others can prep the data the way that they see fit, starting from the raw source. Since it's likely you'll need to process the data in your data lake at least one time, you want to make sure that you treat the original copy of the data as immutable, meaning that you cannot change it once it's been uploaded. You can make copies of the data, but the original data that was ingested remains untouched. You can use S3 lifecycle policies to move raw data to more cost-effective storage tiers as it becomes more infrequently accessed over time. And you can use S3 features like object lock to ensure that no one can modify the raw data asset. Any changes done to the data would be made and then saved into another S3 location used specifically for prep data. The analytical tools can then read the data from the prep data location, not from the raw source location. Leaving the raw source untouched allows you to format it in different ways depending on who is using the data. There are multiple types of data prep that you might create processes for. The first is shaping. Some examples of shaping data is when you select only the fields you need to use for analysis, combining fields or files into one, or otherwise transforming and aggregating data in regards to its shape or schema. For example, you might find that the data is organically ingested across multiple files, but in order to analyze it efficiently, it makes sense to join the data across those files into one main file. Another type of data prep is blending data. This is taking datasets that are originally ingested using different schemas or formats, and then changing or tweaking the datasets so that the schema or format matches in order to analyze it. Then finally, there is data prep that falls under the cleaning category. This is when you are filling in missing values in a dataset, resolving any data conflicts, or normalizing the data to common definitions. With data lakes, you'll likely be doing all types of data prep at one time or another. And with the scale of data that we are talking about here, using automation to prep data is key. Knowing that, what tools exist for data prep in AWS that can be automated? Well, you can use AWS Glue jobs to automatically run scripts that transform data based on triggers or run on a schedule. Or, of course, you can use AWS Lambda functions that get triggered as data is uploaded to your data lake. Just know that spending a lot of time setting up the processes for data prep is normal and will account for a large percentage of the work involved with setting up your data lake. Create transformation processes that can be automated when possible as a best practice. Lambda is best used for transformation of real-time data, since you can trigger Lambdas to run as data comes in, while Glue jobs is best used for processing data in batches. AWS Glue has three main components. We have the Glue data catalog, the crawlers and the classifiers, and Glue jobs. Since we have already covered the data catalog and the crawlers and classifiers in a previous lesson, let's focus on Glue jobs. A job is the business logic that performs the ETL work in AWS Glue. When you author a job, you provide details about data sources, targets, and some other information. The result is a generated Apache Spark API or PySpark script. Then, when you run a job, Glue runs the script that extracts the data from the sources, transforms the data, and then loads it into the targets. This diagram shows the process of creating a job. See the numbers 1 through 6 here that are labeled? We're going to go over each one. First, you must choose a data source for your job. The tables that represent your data source must already be defined in your data catalog. The data source is most likely the raw data before transformation. Next, you choose a data target. This is where the data that gets transformed will be loaded. You can either designate a table from the data catalog to be the target, or you can have the job create a new table when it runs. If you are using Amazon Athena, the tables can point to data sources like a DynamoDB table, an S3 bucket, or a database that requires a JDBC connection. Once the source and target are defined, you then provide customized configurations for your job, and then a PySpark script gets automatically generated for you. Examples of items you configure for your job include what type of job environment to run in. You can run your job as an Apache ETL script, a Spark streaming script, or Python shell script. It depends on your use case which one you would choose. You can choose to let Glue generate a script for you, or you can provide an S3 location with a script that you have already written for the job to use. Another configuration you provide is the transformation type, which can change the schema, which allows you to change the schema of a source data and create a new target dataset. Or you can choose to find matching records. You also configure logging and monitoring requirements. After you provide all of your configurations, AWS Glue generates a PySpark script, and you can then edit this script to add things like transforms or whatever PySpark code that you want to add. Glue provides a set of built-in transforms that you can use to process your data. You can call these transforms from your ETL script. Some examples of built-in transforms Glue provides are things like dropping null fields, filtering records, joining datasets, mapping fields from source to target, and more. Check out the class notes for a link to view all of the built-in transforms that are available. If you are a PySpark expert, remember you can always provide your own script to a job by uploading it to S3 and then just pointing the job to the script. If you are not an expert, you can use the generated script that the job provides to you as a starting point, which you can then modify to fit your specific use case. After you have edited the job to your liking, you then determine when you want the job to run and configure a trigger or set up a schedule for the job to run. Finally, when all of this is done, you will have a script. In the AWS Glue console, the script is represented as code that you can both read and edit. Glue Jobs gives you a great starting point for beginners working with PySpark for the first time, and it runs the script on essentially what is a managed Hadoop cluster. There's lots happening under the hood we didn't discuss in this video. Check out the class notes for more.
As Morgan covered in the last video, data prep is 80% of the processing you do in a data lake. This video has the primary objective of covering some file optimizations you can do to better extract performance and cost out of your data lake. I will cover columnar data formats, compression and splitting, and also talk about Athena partitioning. Get your beverage of choice, and let's begin talking about columnar data formats. Imagine a dataset that looks like this table containing ID, name, and age. Now, imagine that we are using a CSV file for storing this data. Since CSV is row-oriented, it will store the information in disk organized by blocks per row, where the first block contains information about the first line, the second one about the second line, and etc. Now, let's say you want to do the following query. Select average of age from table. This is a query that will need every single value from one specific column. Because the data is stored in a row format, it will require the system to perform multiple disk IOs to get the data needed to calculate the average. In this example, I am matching one row per file system block just for you to get the idea. That being said, the query would need 6 storage IOs because we have 6 rows in the table. On the other hand, this is how data is stored when you have a data format that's storing information in a columnar way. Here, the information is arranged in blocks by column, where the first disk block would have the values 1, 2, 3, 4, 5, 6, the second disk block would have all the names, and the third disk block would have all the ages. Again, I'm abstracting block sizes and matching them with my dataset just to illustrate the difference. If we do the same query, which requires all values in a column, the number of consumed IOs is smaller because the information in the disk is naturally organized in blocks that represent the values of a column. With less disk activity, the query tends to run faster. So we can tell that this type of data arrangement is more optimized for this type of query. But again, there is no better format. Row-based systems are designed to efficiently return data for entire rows. Also, if you're constantly sorting and adding new entries to the dataset, row-based formats can be more appropriate since the pieces of information needed to sort and write is tied together, requiring less IOs. Columnar data store shines for analytics, because for most big data and data lake related queries, you would be interested in extracting values from entire columns. Columnar data formats are also optimized for compression, and let me tell you why compression is strategic for big data world. Compression is important for two main reasons. First, it allows data processing systems to optimize for memory. Most high-performance big data technologies copy data to RAM memory for faster execution, and compressed data would allow you to fit more data using the same memory space. Second, compression is important because in services like Amazon S3, where you pay per usage, one of the aspects taken into consideration for building up the price is the size of your buckets. In other words, compression makes things faster and cheaper, so it is something you would like to have in your dataset. Speaking about cost and performance, data partitioning is also important, especially when you are working with Amazon Athena. That's because Amazon Athena charges you per terabyte scanned. So if we convert our files to appropriate data formats before doing Athena queries, we can make Athena scan less data, resulting in Athena queries that runs faster and cheaper. Columnar data formats are instrumental for Athena usage because, as you learned, data is organized in the form of columns. If you have a data set with columnar data format and do a query that scans entire columns, under the hood, Athena will perform S3 partial get operations, which will get only the specific part of S3 objects that contains the columns you are looking for. That would make Athena scanning fewer data and consuming less memory, again, resulting in a query that runs faster and cheaper. In addition to file formats, compression, and partitioning, there are more best practices I recommend you doing in your data lake. The additional reading of this week contains good information, and don't forget to check it out. In the next video, you will see a demo where I will show you the difference of running Amazon Athena queries against a CSV, which is row-based, and Parquet, which is column-based. Remember, data lakes are still schema on read, which means the processing layers can adapt to the dataset, but optimizations and data prep are highly recommended, mostly because of cost and performance. Alright, in this demo, I am going to show you how to use AWS Glue to transform CSV files to Parquet. In other words, to transform a file that uses row-based format to a file that uses column-based format. Then I am going to run a Glue crawler against the Parquet dataset to create a table in the Glue H catalog. And I am going to be doing the same query against both tables. You're going to see the difference between the query that runs against the CSV dataset and the query that runs against the Parquet dataset. So if we go to Athena, we have the Athena table that had been created pointing to the pointing to the table that uses the CSV file. And that was created by the crawler demo you saw on the last week. If we click here on those three dots and click in create, generate create table DDL, it will run this query against Athena, which will show you how was the create table command. So you can see that it is using a CERD that is a CSV CERD, right? It points to the location S3 TLC ref demo, which is the location where I have that CSV file. And now I want to run a glue job. So let's go to AWS Glue and find the jobs here on the sidebar. Jobs. Here. So I am going to add a new job. And this job will be called CSV to Parquet. I need to use an IAM role, and I already have an IAM role previously created here called AWS Glue Service Role Glue Jobs. This role is an IAM role as the other one I showed you, but this one has access to also do put objects, because what this glue job will be doing is getting objects from bucket A and putting objects into bucket B. So this role is allowed to put objects and get objects, and also allowed to use KMS keys if needed. In this case, I'm not doing encryption, so I don't need the role to interact with Key Management Service, KMS, but it is there just in case. Now it is going to run a Spark job. Here I can choose what is the Spark version, the Glue version, right? And here is the most interesting part. I want Glue to propose a PySpark script for me based on what I click in this wizard. So this is where the script will be created. Here you can see monitoring options. You can enable job metrics, continuous logging, and Spark UI for monitoring. Because under the hood, what will be happening is the execution of a PySpark script in an EMR cluster. But that's fully serverless, so you don't see that cluster. But you can have the access for the logging in a CloudWatch log stream that you choose, or in an S3 bucket that you choose. Here I'm going to click Next. And here I should choose a data source, which in this case is a table on the Glue H catalog. It is the only table I have so far, which is the table that had been created by the crawler you saw next week. It points to S3 TLC ref demo, and the classification is CSV. Now I should choose a transformation type. In this case, change the schema. And I need to choose a data target. I will ask the Glue job to create a new table as a data target, and the data store is Amazon S3, and the format is Parquet. And here is where the job will do the data transformation from whatever it gets, which is CSV, to the format I choose, which is Parquet. Here I'm going to choose my target path. Yeah, and I am going to save the output of this Glue job under Parquet files in my S3 bucket. Here is where I could choose some sort of data transformation in terms of the content of the file itself. I can reorder them on the files that will be stored as the output, and I can remove some fields as well. I will leave it as is, because the main objective here is to have a one-to-one conversion CSV to Parquet to do an Athena query to different tables pointing to the different datasets containing the very same data. Save job and edit script. Now notice something interesting here. This is a PySpark script. And as you can see, you don't need to have PySpark knowledge to operate this, at least on the very basic level. If you click here, you can reorder those elements, and this what you see is what you get kind of graphical user interface. And if you click here on the transform name resolve choice, it highlights the part of the PySpark code that will be doing that specific action for you. So it is applying the mapping, it is resolving choice, and it's dropping null fields, and it's storing on the path S3 TLC ref demo Parquet files. And you can see that this is the actual line that is doing the right. So it is glue context, right dynamic frame from options. This dynamic frame is something that regards to PySpark. So you don't need to understand PySpark to operate these on this basic level, which is just CSV to Parquet transformation. And here is where the connection options, format, Parquet, because that's what we had selected. So save, run the job, and now we can have a coffee, we can sit in our chair, wait a little bit, the job is running, and you can see the glue job running because when we click here and we expand and we see the history, we see that the jobs are running. As I said, the logs and the error logs are available in CloudWatch Logs log streams. So if you click here in the error logs or in the logs, you will see the logging information for this job in CloudWatch Logs. This job is initiating a Hadoop cluster, so it takes a couple of minutes. The log group does still not exist because this is the first time I'm running this job. So it is asynchronous. It is creating the Hadoop job right now, and it should take around 5 to 6, maybe 7 minutes to complete. So after 2 minutes and 9 seconds, it was actually quicker than I thought, the job had succeeded, and I can see that the job succeeded because of the run status here. Now if I click here in logs and error logs, let me click in the logs for you to see. I am linked to the CloudWatch Logs console, and here I have all the logging information about that specific run, about that specific job run. So you can see, if you scroll up, that there are things that are actually regarding a Hadoop cluster. If you're familiar with Hadoop, you will recognize those type of informations available in those logs here. But the most interesting thing that I want to show you is, if I go on my S3 bucket, which is the bucket that I am using for my dataset in this example, and I click in TLC ref demo, now there will be a new folder in that bucket. Now there will be a new prefix here, which is the Parquet files. So what this job did was basically getting this CSV file here, 733 megabytes, and stored into a columnar file here in this prefix. So here you can see that it split the file in multiple chunks, which is a good practice regarding Athena queries and data lakes, because you allow that data set being got in parallel by multiple download threads. And you can see that the total file size is about 150 megabytes. So you can see that this specific data set had been converted into something that was 700 megabytes to around 150 megabytes, which is 5 times less. In a storage solution where you pay per size here, like we have in Amazon S3, you can see that how this would impact your budget. It's 5 times less. And also, the most interesting thing comes when we want to do Athena queries. But before doing Athena queries, we need to crawl that data from that new dataset Parquet files and having the glue crawler creating another glue table on the glue H catalog. So let's quickly do this. Crawlers. I could use the same crawler as I used the last week, but I'm gonna add a new one. And this second crawler will be called TLC crawler Parquet, because it's a crawler that will crawl against the Parquet files and will infer the schema and create the glue table on the glue H catalog. TLC ref demo now Parquet files. So now I am instructing the crawler to go on this bucket and on the Parquet files, which are exactly where my Parquet files are located. Next, no. Choose an existing IAM role, the crawler role, which I had created on the previous demo. Next, run on demand. Now, same database, TLC. And now, next, finish. TLC crawler Parquet, run crawler. The crawler is actually faster than the job because the crawler is just doing a get object, partial get object, getting the first 100 or couple of thousands of lines, and creating the Athena table for you, the glue table on the glue H catalog, which can be understood as an Athena table. So here it is starting. If we refresh, it doesn't take too long. So this crawler is already stopping because, as we can see, it took 1 minute to run and it added one table into my glue H catalog. Let's go to the glue tables and let's see, we should have two tables here, which is the Parquet one and the TLC Ref Demo one. This one points to CSV, this one points to Parquet. If we click in this table, we can see the table properties and we can see that it is using the Parquet CERD. Remember the story when I said that if you try to see a DVD in a VHS, you would have errors because you're not using the proper CERD? So here we have a data set that is in Parquet, and we are using the Parquet CERD, right? So we should not have errors when we go to Athena and query this table. Now let's go to Athena and query the table. Athena. And these are the two tables. And the first query I'm going to do, I already had the query here on my clipboard, so I just pasted, select average of fair amount, which is one of the fields in that CSV file or the Parquet file dataset, and also the average of tip amount. Remember, this is a New York City TLC, Taxi and Limousine Commission, TLC, trip record data. So we have things like passenger count, trip amount, and then we are going to run this query against the CSV file. And here we have, for that specific data set, which we have regarding the year 2018 and month 06, June, the average of fair amount was $13.25, and the average of tip amount was $1.09. You can see which is approximately 15%, which is basically 15 to 18%, which is what people from New York City usually tip the taxi drivers. So now let's do the very same query against the Parquet dataset. So I'm just going to replace this table by the table called Parquet files. Run query. Query is running. You can already see that the query run faster, right? And same results. Now, if we go here on Athena and click in History, we can see that the query we made against the CSV dataset scanned 800 or almost 900 megabytes, as you can see here. And it took 2 seconds and 21 milliseconds, 2.21 seconds. The query made against the Parquet dataset run faster. And here is the most important thing. 20 megabytes scanned. That's because it only consumed the data from a specific column on the file. All right? So that's it. That's how you can see on how using glue jobs to transform your files from row-based formats like CSV files to column-based files like Parquet files is very interesting and very important for your data lake architectures. See you on the next one, and thank you for watching.
In this video, we are going to focus on the security and compliance aspect of setting up your data lake. When using a data lake, you will likely have multiple teams using various technologies to analyze the data. People will have different roles, and therefore will have different uses for the data lake, and will likely need different permissions. The data scientist needs programmatic access to S3 directly so that they can run their custom processing jobs, whereas the analyst wants to visualize a subset of the data using a tool like Kibana. Another use case could be a business person who just wants to be able to search the data lake for documents to view what sort of data is available. These are all different consumers of the data in your data lake, and you want to scope data access and permissions in a granular way that fits the use case for each individual role. Consumers aren't the only reason you need to scope access control. You also have producers for data. The ingestion mechanisms in place would have their own set of permissions. The security of your data lake would treat these two entities differently in regards to security. Given that there are a lot of different roles, producers of data, consumers of data, and tools accessing the data in the data lake, it is first important to understand the access patterns for the data, and then you can shape your security around these patterns. It's also important to consider that your data lake might contain sensitive data. You'll need to be aware of what compliance programs you need to adhere to. Compliance involves creating and applying data access protection and compliance policies. For example, if you are storing personally identifiable information, or PII, you would want to restrict access to it so not just anyone can view that information. You would want to encrypt all of the data and keep audit logs of who is accessing the data and when they are accessing the data. Different types of data adhere to different compliance programs. Securing your data lake and adhering to compliance programs can be a big task. You need to secure the storage layer, the cataloging mechanisms, and the services that process and analyze the data. Instead of trying to tackle this all at once, you should look at each individual building block and secure them, focusing on one at a time. It's important to remember the shared responsibility model as we go through some of the examples of the security measures that you can put in place. Security is a shared responsibility between AWS and you. The shared responsibility model lays out who is responsible for what when it comes to security in AWS. AWS is responsible for the security of the cloud, and you are responsible for security in the cloud. You don't need to secure every single aspect of every single service. Much of the most basic security measures are taken care of for you by using managed services. Depending on what services you are using, you will have varying levels of involvement in securing those services. Let's run through some examples. First things first, you need to set up some basic security guardrails for S3. The goal here is to take preemptive measures to protect data before you allow anyone to access the data lake. One example of a guardrail that you can set up is enabling encryption on your S3 bucket. Encryption for data in transit is enabled by default, and it's a free feature. For data at rest, enabling encryption is as easy as checking a checkbox. And if you choose to use the default encryption option, you can feel good knowing that S3 uses AES 256 encryption keys. With default encryption, you upload the data to S3, and S3 manages both the encryption and decryption of the data. You can also choose to use your own custom keys or use a key that is managed by AWS Key Management Service. Another example of a guardrail that you can configure is the S3 bucket access policy. S3 allows you to restrict who can access your data and what actions they can take on that data through the use of a bucket access policy. Bucket access policies are similar to AWS IAM policies in that they are both JSON-based. Here's an example of a bucket access policy that restricts via IP address range. Though you can also restrict by VPC, HTTPS, or other AWS services. You want to create policies that force users to access the data through an approved channel, not open to the public. In most cases, you don't want your data in S3 to be public, and S3 by default is private. That being said, it is wise to make sure you are using the block public access setting that S3 provides, which will override any other configurations that would otherwise make data public. Now let's take a look at another common component of a data lake, AWS Glue. As far as data protection goes, AWS as a whole provides secure sockets layer or SSL encryption for data in motion. So the communication between services and AWS Glue is encrypted by default. To secure the AWS Glue data catalog specifically, you can enable encryption at rest for the metadata that it collects and indexes. From an access control perspective, you would take advantage of IAM policies that would explicitly allow or deny actions to AWS Glue. You should even scope your permissions to the specific AWS Glue API calls. For example, one type of user might need to access the data catalog and nothing else, whereas a more involved user might need to access the data catalog as well as Glue jobs. You want to ensure that you are scoping your permissions accordingly in IAM. Beyond assigning permissions to users, groups, or roles in IAM, you can also create resource-based policies as an extra layer of protection. Here's an example of a resource-based policy for AWS Glue. In order for a user to have access to a resource in AWS Glue, they would need access granted from their associated IAM permissions in addition to the resource-based policy allowing them access. The same security concepts that exist for AWS Glue exist for other AWS services used in data lakes. You want to make sure you explore how each individual service supports security for data protection and access control. For example, Amazon Athena and Amazon Elasticsearch Service both support resource-based policies and IAM-based access control, like most data lake-related AWS services do. Different teams, users, or environments will have different access permissions. You should be diligent in assigning permissions using the principle of least privilege, where each entity only gets the access they need and nothing more. This includes validating security requirements based on data classification and verify data producers and consumers have appropriate access. And finally, you should run audits to ensure that things are going according to plan. In regards to compliance auditing, I would recommend that you enable S3 server access logs alongside AWS CloudTrail to capture how users and entities are accessing S3 resources, as well as API calls in your AWS account. Logging this sort of data can be very useful for auditing. Actually, speaking of CloudTrail, if you have an existing AWS account with CloudTrail enabled, you can use Athena to query your CloudTrail logs with SQL, and then use this data as a dataset to begin exploring AWS Data Lake services. So remember, as you go about securing your data lake resources, you want to check each individual AWS service for how it handles data encryption in transit and at rest, access controls, IAM permissions, and other security features which will vary from service to service. Keep the shared responsibility model in mind and rely on security features built natively into AWS, or use services like AWS Lake Formation to make it all easier to manage. Check out the class notes for more information on security and lake formation. Data that is stored in a data lake isn't easy to digest from a human perspective, even if it's cataloged and indexed correctly. Data is generally formatted to be read and used by technology, code, services, tools, not the human eye, especially when you are talking about data at scale. The more data you have, the less likely it is you'll be able to just read text-based documents and make sense of the data. What you need is a way to utilize this massive amount of data to help you make better business decisions, make predictions, and identify patterns as well as outliers. Visualization is what you need. Data visualization is taking abstract data or data that is not easily digested and understood, and representing it in a visual and interactive way to enhance understanding and to derive insights. Consider this example. Let's say you own an e-commerce website, and you are trying to track how your users interact with your website. You might decide to ingest clickstream data into your data lake. The goal of you collecting this data is to figure out where to invest time and money in enhancing the user experience for your website. Clickstream data is information that a user leaves behind while visiting a website. The data captured is typically captured in some type of log file and contains things like dates and timestamps, IP addresses, URLs, and more identifying information. Instead of trying to sift through all of these data points by reading through them, you can visualize the data to better understand it. Without visualization, this data would be almost useless. One way to visualize this type of data is called a click map. At a basic level, a click map is a visualization of how users browse a website. It shows how users scroll, click, and move their mouse on the website. You can see what areas of the site are used most versus what areas of the site are largely ignored or not seen. You can use third-party software that would access the clickstream data being stored in S3, then generate your click map, which would show you how your users interact with your website. You can then use this click map to determine where to place advertisements or new features. Now let's talk about a simpler example. Let's say you run a chain of restaurants, and you want to use the data collected by each branch of your restaurant to determine key business drivers. You could take the data that was collected by each branch, like sales, visitors, reservation data, and the financial reports, and you can visualize that data to compare each branch against each other. You could use line or bar graphs to view sales by day for each restaurant. This data by itself would be interesting to visualize to gain insight into how each branch stacks up against each other. But if you brought in external data, like traffic patterns, weather patterns, economic data from the areas the restaurants are located in, or other types of external data, you could then start to visualize these data sets side by side and try to identify any patterns that might indicate business drivers. For example, you might find that areas with increased foot traffic have higher sales than areas with a lower foot traffic. Or you might find that areas that experience more warm, sunny weather also correlate with higher sales. These sorts of insights can help drive business decisions, like where to open the next branch of your restaurant. As you can see, the raw data assets by themselves aren't incredibly useful to us mere mortals. You need tools that help you make sense of the massive amount of data that you are collecting, and visualization is an incredible and intuitive way to begin to derive insights from your data, explain patterns in that data that were not previously noticed, or even identify outliers in your data that are potentially skewing results. We will continue to explore this topic coming up next. In this video, we are going to explore the data visualization service Amazon QuickSight. As you've learned, data visualization is important for understanding your data and using data to make decisions or identify patterns. From a high level, this is the process when using Amazon QuickSight. First, you connect to the data that you want to analyze. Then, you can optionally use QuickSight to do some fine-tuning of the data to optimize it for the visualization layer. You can add calculated fields, apply filters to the data, or change field names or data types. If you are using a SQL-based data source, like a relational database, you can also use the data preparation feature to join tables using SQL. You then save this preparation as part of the dataset. Once the data is in the optimal format for QuickSight, you then create data analyses, which are visual representations of the data. You tweak your visuals and organize them into dashboards. You can share this dashboard with others to explore. From there, you use the insights derived from the dashboard to make better decisions for your business. You can use multiple different types of visualizations depending on your needs, such as comparison and distribution visuals, bar charts, time series graphs, line graphs, scatter plots, heat maps, and more. There's a lot of options when it comes to how you can visualize your data. Picking the right data visualization for your dataset will be important for deriving insights. So make sure that you explore them and have an understanding of what is offered so that you can pick the right one. For example, let's say that you work at an electric company and you are trying to visualize the consumption of electric over the last 90 days. It wouldn't make sense to try to use a pie chart for this. It would make more sense to use something like a scatter plot to plot the usage for each meter each day. Then you can see the correlation between the date and the usage. If for some reason you see a spike in the usage on, say, August 2nd, then you can go dig into why that may have happened. Perhaps there was a heat wave that caused everyone to turn on their air conditioning units. No matter the cause, once you identify the outlier, you can then do more research to figure out why it happened. You could also use this data to try to predict future electric usage with the help of machine learning models that use external data like weather forecast. You could derive insights that correlate electrical usage with weather data. Now, what if you aren't sure what visualization will fit your needs best? Well, QuickSight has a feature called Autograph that will select the most appropriate visualizations based on the properties of your data, based on things like the number of elements in a set and the data type. This can often be a good starting point to get your head wrapped around your data and to help you come up with more ideas on what QuickSight can do to help reveal relationships and patterns in data. You can create dashboards in QuickSight with multiple different visualizations together to show a well-rounded view of the data. Now, what really differentiates QuickSight from other business analytics tools out there is this: the native integrations that make analysis seamless, the scaling mechanisms that just work, and the ability to perform ad hoc transformations and analysis. And finally, a feature that allows you to speed up your analysis using something called Spice, which does make QuickSight special. And we will go into detail on Spice in a bit. Let's first start with the integrations. The data you visualize with QuickSight can come from a variety of data sources. It integrates natively with other AWS services, like, you guessed it, S3, but it also supports data sources like Redshift, Amazon Relational Database Service or RDS, and others. On top of integrations with other AWS services, you can also import data to QuickSight from CSV and Excel files, SaaS applications like Salesforce, or even from on-premises databases. Another integration that makes QuickSight an innovative BI service is its integration with the machine learning service Amazon SageMaker, which we touched on in an earlier lesson. There is an Augment with SageMaker option that you have when you select your data source, and from there, you can pick the machine learning model that you want to use from a pre-populated list of SageMaker models, provide the schema of the data for input and output and configuration settings, and start running the data through the model that you have chosen. It's really a seamless way to begin using machine learning using the data from your data lake. Check out the class notes for more information about machine learning and QuickSight. Moving on to scaling. This is a key differentiator of QuickSight when comparing it to traditional BI solutions. Traditional BI solutions often require teams of data engineers to spend months building complex data models before generating a report. They typically lack interactive ad hoc data exploration and visualization, limiting users to canned reports and pre-selected analytical queries. On top of this, they also require significant upfront investment. And then, as you continue to grow the dataset you are analyzing, you need to keep building out more storage and compute to handle the scale of the data. With QuickSight, since it's a managed service, this is taken care of for you. All you need to do is point QuickSight to the data source, and from there, the scaling is automatic. Whether you are creating visuals for 1 gigabyte or 10 terabytes of data, QuickSight can automatically handle the change in data size. This greatly reduces the overhead cost and complexity perspective when comparing to traditional BI tools. Talking of the constraints of traditional BI tools brings me to my next point. QuickSight allows you to run ad hoc analysis on data. You don't need to provide users with only a predefined view of the data. Instead, you can dynamically change the visual representation of data and explore it in new ways easily. And finally, one feature that really spices up QuickSight is it uses something called SPICE, which stands for Super Fast Parallel In-Memory Calculation Engine. SPICE is designed to perform advanced calculations and serve data quickly. The storage and processing capacity available in SPICE speeds up the queries that you run against your imported data. By using SPICE, you save time because you don't need to retrieve the data every time you change an analysis or update a visual. The built-in computation engine allows this to happen on the fly without having to rebuild everything just to change what you're looking at. Coming up next, let's jump into the AWS console to explore QuickSight using the New York City taxi data Raf had used for previous lessons. Now that you know some of the basics about Amazon QuickSight, let's go ahead and jump into the AWS console and get a look at how this really works. As you can see, I've already logged into my AWS account and I've already navigated to the Amazon QuickSight service landing page. And you can see that there are a couple analyses that I already have loaded into this account. Most of them are samples. So what I want to do is, instead of just showing you a sample, I want to visualize the New York City taxi data that Raf had used in previous lessons. So I want to look to see if we can identify any patterns, any outliers, just make more use of that data than the raw data that's being hosted. So what I want to do first is add a new analysis. And from here, we have a list of data sets that I could use for this analysis. I want to add a new data set, so I'll click the New Dataset button. And from here, you can choose what your data source is. So where is this data coming from? Well, you have the choice to upload a file yourself. This could be a CSV, JSON file, an Excel sheet. So if you have data that's downloaded on your local computer, you can upload it that way. You can import data through Amazon Athena, relational database service, so you can bring in data sets from a database, Redshift, SQL Server. You can also bring in data from external providers like Snowflake, Twitter, Teradata, GitHub, things like that. But the data that we're looking at comes from the Registry of Open Data, and so therefore we are going to select S3 as the data source. So I'll go ahead and do that. And here we have to give the data source a name, which I will name it New York City Taxi. And then you have to upload a manifest file. So if we click on this, this will tell us what a manifest file is. So you'll notice that in the AWS console, there's often little hyperlinks that you can click that it will give you more information in the documentation. So that's what I did there. And here it shows you what a manifest file is. A manifest file is a JSON file. And a manifest file will specify what data files your data source is coming from. So for us, we have an S3 data source. This is basically going to show QuickSight what prefixes to look for, what different files to pull this data from. So I'll go ahead and exit this. And what we're going to do is we are going to upload a manifest file. I already have one created on my local machine. So I'm going to go ahead and open that up here, this nyctaxi.json, and then I will click connect. So now what's happening is it's finished the dataset creation. It went through and kind of scanned everything that was in that manifest file, all of the different files that I had in there. And now what we can do is we can edit or preview the data. And this would load the data here in this preview format that you could then go ahead and look at it. So this gives you the opportunity to do any sort of data prep that you need to do before you do your visualizations. So what I mean by that is sometimes the data is in a great format for different analysis tools or processing tools, but the data isn't in the most perfect format for visualization. So this gives you the opportunity to tweak things to make it specifically formatted for QuickSight. So you have the ability to do that here. You also have the ability to add calculated fields, as you can see this button here. And we don't have any sort of data manipulation that we want to do right now. So we're going to go ahead and just accept it as it is and import it. So I'm going to go ahead and click save. And now you can see that we have a data set called New York City Taxi. And we have the owner is me and last modified a few seconds ago. So that's good. That's the one that we want. So now what I want to do is click Analyses. And then I want to select a new analysis. And then you get to select what data set you're creating the analysis for, which is New York City Taxi. And now what I want to do is click Create Analysis. All right, so this brings us to this page here, which allows you to configure the analysis that you are trying to create your visualization for. And so you can see here, we have this number where it's like importing. So it's importing all these different rows of data from our data source. And you can see already that we're looking at about 4 million rows being imported into Spice. If you remember, Spice is that extra compute power that allows you to do things like speeding up your queries, and you can change visualizations on the fly without having to rebuild everything. So we're importing all of the rows in the New York City Taxi dataset into Spice and into QuickSight that we can then create an analysis for. So we'll go ahead and just wait and let that finish. Now the import is complete. And if you look here, you can see that there are almost 9 million rows, so 8.8 million rows that were imported from that data set. So we're talking about a lot of data here. So what I want to do now is I want to create an analysis that allows me to view the number of rides per day. So that way I can look at trends and things like that. So what I want to do is first I'm going to choose my visual type, which if you look down here on the left-hand side, there's a bunch of different things listed. If you hover over it, it will tell you what type of visual you're looking at. So there's a key performance indicator visual type, a gauge chart, a donut chart, pie chart, a bunch of different bar charts here, some line charts, some area line charts. We also have pivot tables that you can use. There are heat maps. There's also a tree map, a scatter plot, a histogram, points on a map, or a word cloud. So you can see that there's a lot of different options that are listed here, and you want to choose the right one for your data. So if I'm looking to analyze data over time and then use it to identify trends, I'm probably going to be looking at a bar chart. So I'm going to go ahead and select a bar chart. So you just go ahead and click on bar chart. And then you have to define at least an x-axis here. So I'm going to choose the date time to be the x-axis. And then you can see it went and created a bar for each day. And then I want to have the value to be the passenger count per day. So I'm going to go ahead and add that there. And now I'm going to go ahead and expand this, make it larger. And so we have a better idea. We can look at this. And if I go ahead and just zoom in on a part of this, you can kind of see the trends that we're looking at. If I hover over January 1st, 2018, we're looking at 32,499 passengers were riding in taxis that day. And then I can kind of go day by day. On the second, 31,662. So no real big statistical difference there. And then we have the third, which is 35,692. So again, that's right in the same vein. And then notice how on January 4th, there's a drop, a very significant drop, where the passenger count drops to only 8,688. So by looking at this, I've already identified an anomaly. So as you can see, visualizations help you identify patterns and trends as well as anomalies. So I'm looking at this, January 4th, 2018, and I'm kind of wondering what happened on that day. So what we're going to do is we're going to go ahead and zoom out here. And then let's open up a new tab and let's Google that day. January 4th, 2018, New York City. And then you can see the first thing that comes up is January 4th, 2018, there was a blizzard. So blizzard conditions occurred Thursday, January 4th, 2018, over Long Island, as well as portions of New York City. So that would really explain why there's this drop in pickups for that one particular day. So this is a great example of how data visualization can help you identify anomalies. Now I'm going to go ahead and minimize that. And next, what we're going to do is I want to use this data and I want to use QuickSight to see how many trips have how many passengers. So out of 100% of the trips that I have, what percentage are only picking up one person? What percentage is picking up two people, three, so on and so forth? This sort of data can be interesting because there's ride shares that are very common nowadays. And with the New York City taxi data, we can see if people are taking advantage of multiple people splitting a cab, basically, or if we're really looking at one or two people taking a cab somewhere. So what I'm going to do now is add another analysis. So I'll click plus here, add visual, and then I'm going to select pie chart. Then I'm going to add a dimension over here, which is the passenger count. And then we can expand this visual. And you can see that we have 85% of the trips recorded, or we're only picking up one passenger. And then we have 8% for two passengers, and then it just gets smaller from there. So you can see that people aren't really splitting cabs very often. 85% of the trips were for one particular person. So ride sharing, for the records that we have, is not happening very often. I'll go ahead and minimize that now. And so you can see that we have these two visuals side by side. It's giving a little bit of a more well-rounded picture of the data, being able to view these sorts of visualizations together. Once you have all of your visuals configured the way that you want to have them, you can go through and then share the dashboard with others to view it. So if I click this share button over in the right-hand corner, and then I say publish dashboard, I can then create a new dashboard. I'm going to call this New York City Taxi Dashboard. Click publish dashboard. And then you can share it with users if you want to. I'm going to go ahead and just exit out of this. Select sheet 2, because that's where we created our visuals. And here now you can see that we have the sum of the passengers by day, as well as the count for the passenger count. So what percentage of the rides had X number of people. So from here, you can then share this dashboard with other users in your AWS account. All right, so that was a really simple example of using Amazon QuickSight to identify trends and anomalies, as well as get a more well-rounded view of the data. Remember that there's a lot more you can do with Amazon QuickSight, so please check out the class notes to learn more about this awesome service. Now that you have some of the foundational knowledge for building data lakes on AWS, you might be excited to get started and experiment on your own. That's awesome, but you're going to need some data to work with. The registry of open data on AWS is a great place to start and search for public data that you can use to try out some of the technologies and techniques that we've covered in this course. The registry of open data on AWS exists to help people discover and share datasets that are available via AWS resources. Data is registered and shared from a variety of data providers that you can access and use to derive your own insights. This idea of sharing data openly helps enrich the data community as a whole and allows you to spend less time capturing and acquiring data and more time running analysis and extracting value from the data. The sharing of these large datasets also provides amazing learning opportunities, as you can focus on learning all the new AWS services we taught you about during this course, instead of working on finding data. The registry also lowers the cost of research because you can run analysis directly on the data from the registry without needing to store your own copy in many cases. Now, that being said, some datasets will be in a format that is useful for your needs, while others may not be. You should be prepared to sanitize data when necessary to clean or otherwise process data to be compatible with the tools that you plan to use for analysis. We actually used the New York City taxi dataset, which is registered with the Registry of Open Data, which made our process for developing these demos to showcase the AWS services much easier and faster than if we needed to find and collect all of that data by ourselves. Now, let's go ahead and explore the registry of open datasets together to get some ideas. You can see that I'm on the Registry of Open Data on AWS homepage here. And in the left-hand side, you can read about the Registry of Open Data. And if you want to get even more information, you can click on this link, and this will take you to the homepage of the Open Data in AWS, and you can read more about it, watch some videos about how other people are using these data sets and things like that. So the About is up here. You can search through the data sets, or you can add a data set or an example of how to use the data set with the registry down here. So what I want to do is search the New York City data set, since that's the one we've been looking at. And if I click details, this shows you a description of the data set. So this is data trips taken by taxis or for-hire vehicles in New York City. You can see that it's updated as soon as new data is available to be shared publicly. There is a terms of use license that you should explore. And then there's also some extra documentation that you can read through as well. So I'm going to go ahead and just open that up. And you can see that this took us to the Taxi and Limousine Commission. So this is not actually AWS's data, right? This is data that an external entity has decided to share on AWS that you can then use. So you can read about all of this information from their website. That's where the documentation is going to live for this. So I'm going to go ahead and go back to where we were. One of the most important things I want you to take away from this video is this usage examples section down here. So you can come into this usage section and see how other people have already used this data set, and then you can try to follow the tutorial yourself, and that will really help you get a better grasp on how to use the AWS services and big data type things in general. So if we click on this optimizing data for analysis with Amazon Athena and AWS Glue, well, that's very similar to what we've done in this course. So I'm going to go ahead and click on this, open the link in a new tab, and this takes us to GitHub, where you can then follow the README that tells you exactly how you can use this data set with Athena and Glue. So this is really an awesome place where you can go get examples and really specific instructions of how to use this data, also how to use some of the AWS technologies. Another really important thing to note is the resources on AWS that support this data set. So you have what is the file type. We can see here that these are CSV files, so that's really good to know. You can also see that it's hosted in S3, and then it gives you the ARN or the Amazon resource name for this S3 bucket. You're going to need this to create things like your manifest file for QuickSight, which is what I did. And then it also gives you the region. So what AWS region is that S3 bucket in? Well, in this case, it's in US East 1. If we now go back to the homepage of the Registry of Open Data in AWS, you can just kind of scroll through here and see all of the different data sets that we have to offer. There are quite a bit of them. So if I search NASA here, you can see we have 8 matching data sets from NASA. So that's really cool. You can go in here and use this data that is transiting exoplanet survey satellite data, right? So you can take that and run your own analysis and visualization and processing on it. So that's really, really cool. I encourage you to go out and build your own data lake. It doesn't have to be big, and using these open data sets can act as a starting point as you begin your experimentation.
Welcome to the third exercise of the Introduction to Designing Data Lakes on AWS. This is an exercise where you are going to use AWS Glue to process data. You're going to define a database and configure a crawler to explore data in an Amazon S3 bucket. Then I'm going to create a table, then transform the CSV values into a Parquet and create a table for the Parquet data. Finally, I'm going to query the data with Amazon Athena. This lab starts with asking you to download a CloudFormation template. This CloudFormation template is necessary because it creates the necessary IAM roles that will be used by the lab environment. This is the CloudFormation template. It just creates a role called AWS Glue Service Role Default. You're going to see that role in the middle of this exercise walkthrough, and it also creates an S3 bucket. So let's start by going to CloudFormation and creating a new stack. So I already have the Web Management Console for CloudFormation, and I am going to choose Create Stack with New Resources. The template is ready, and I can upload a file from my computer. So I can choose a file and do exercise 3, processing, next. Then I am going to provide a stack name, such as, for example, exercise 3 processing. Go next, scroll down, next, then scroll down and acknowledge that this AWS CloudFormation might create IAM resources with custom names, which is the role that you just saw. So now I am going to AWS Glue while this CloudFormation template is being created. If we want to inspect the creation of the CloudFormation, we can choose resources and see what the CloudFormation creates. It's creating an Amazon S3 bucket called glue-B74674C0. It's a random name, and it's also creating a role and created the role, and it's creating some internet gateway, some default lab resources that we create. But what we want to go is AWS Glue, and in the navigation pane, in the data catalog section right here, I can choose databases. So I'm going to choose the option database and choose add database. This database name will be New York City Taxi. That's the database name we suggest creating, and I'm going to choose create database. Then in the navigation pane, I can choose tables, and I can create tables using crawler. So you can add a table manually or by using a crawler. These crawlers are programs that connect to a data store and process data through a prioritized list of classifiers to determine the schema of your data. So Glue provides classifiers for common file types such as CSV, JSON, Apache Avro, Parquet, and others. You may also want to use your own classifier, but we're just going to choose add tables using Glue crawler. And for the crawler name, I'm going to put New York Taxi Crawler. Choose next. For the crawler source type, I'm going to choose data store and then choose next. Then add a data store, and I am going to specify the following S3 path. S3 : / AWS TC Large Objects, Dev AWS MO Designing Data Lakes Week 3. This is an S3 bucket that we provide that contains data files, which includes data for all rides from the green taxis in the New York City in the month of January 2020. I'm going to keep all the values on the defaults and add an S3 data store. Then I am going to hit next, and in the IAM role, I'm going to choose an existing IAM role, and I am going to type AWS Glue Service Role Default. That is a role that got created by the CloudFormation template, so that's why we need to run the CloudFormation stack first. Then next, on the target database, I'm going to select the database that we just created, and then choose next. I review the configuration and create the crawler. Now, we just created a crawler that will go on that S3 bucket from AWS training, get the files, infer the schema, and create a table for us. If we go to tables and we keep refreshing that, once the crawler runs, we will be able to see a table here. Crawler is ready. I can enter in the crawler and choose the option Run Crawler. So the crawler is going to run, which means that crawler is going to that S3 bucket, getting the data, inferring the schema, and then creating the table for me. It should take a couple of minutes for the crawler to run, but I can wait. In my case, the crawler took 52 seconds to run, and it's now completed. So if we go on the tables, we should see a table created in our database, and it's a table that has the name week 3. If we click in that table, we can see the properties and we can see the schema of that data. This comes from the bucket, and the crawler created a table that matches the schema of the data that is in the bucket. Now, as part of the second task, we are going to transform data from CSV to Apache Parquet, and we are going to use ETL jobs for that. So I'm going to the navigation pane. In the ETL section, I am going to choose Jobs. And then it opens a new browser tab with AWS Glue Studio, which is what just happened here. In the Create Job section, I will keep everything in the defaults and choose Create. Now in the job diagram, I am going to choose Data Source S3 bucket. And in the right pane, I am going to keep the data catalog table here. But the database, I will choose the database New York City Taxi, and the table will be the week 3 table. In the job diagram, on the left side, I'm going to choose Data Target S3 bucket. And now I am going to format that as Parquet. So the S3 target location will be S3 : / and then the bucket that got created. I can just browse Amazon S3 and choose the bucket from here. This is the bucket that got created by the CloudFormation template. So I'm just going to choose that bucket. And at the top of the pane, I'm going to choose Job Details and specify a name for that job. New York Taxi Parquet, and the IAM role I am going to choose is the one that got created by the CloudFormation template, AWS Glue Service Role Default. I'm going to scroll down and expand the advanced properties, and the script file name should already be New York Taxi Parquet.py. I'm going to save this job. So now the job is saved. We can choose script. We can click on the script tab and see what is the actual PySpark template that will do that data transformation for us. And we can see that our columns that got created by the crawler, because it's indexing a table and because it's a service that integrates with the source and the destination, it is going to apply mappings to the schema that matches that table, and it is going to use the Glue Parquet format and save that into S3 on that specific bucket. So you can see that when I go on job details and I click in the console and I select things all around, it updates a script for me. So I can save and run that script. Now my Glue job is running, meaning that something is getting this data from the bucket and converting to Parquet and adding to another bucket. So the job is started. We can go to jobs and refresh and see the job name, and we can see the runs, and we can see that we have this job running right now. It should take a couple of minutes to run, but we can wait. Once our job finishes running, we can see that the run status is succeeded. Then what this Glue job did was getting data from one bucket, converting to Parquet, and saving into another bucket. So what we are going to do now is going back to AWS Glue console, and then we are going to crawlers, and we are going to create another crawler, but this time we are going to crawl the data using the Parquet data. So I'm going to add a new crawler. For the crawler name, I'm going to put New York Taxi Parquet, choose next. And for the crawler source type, I'm going to add a data source, which is the bucket that got the files in Parquet. So I'm going to choose that one. Add S3 data source. Then I am going to choose the IAM role, that is the AWS Glue Service Role Default. Same thing, I'm just creating another crawler. Going to choose next. Then target database, New York City Taxi. I'm just going to hit next because it will create the table for me, and then create crawler. I can refresh. The second crawler will be there. Once we create the crawler, we need to do run crawler if we want the crawler to run immediately after. So it will run the crawler. Again, it should take a couple of minutes. This crawler will be getting the Parquet data, will be inferring the schema, and will be creating a table out of that. Once these two tables are created, we are going to query data from one table, and we are going to do the very same query to another table. And you're going to see the difference in performance. So we should see two tables when this crawler finishes. So the crawler is still running and the tables are not there yet. We just have the week 3 table, which is the one that uses CSV. If we want to see the crawler running, we can go to crawlers. New York's Taxi Parquet, it's running. And we can go scroll down and see that the crawler is still running. I can wait. When our second crawler runs, we should see status completed. And if we go and see the tables, now we should have 2 tables in the New York City taxi database. The week 3, which uses CSV, and this table called glue_hash, which uses Parquet. Now I am going to Amazon Athena, and I am going to do queries against these 2 tables. And I'm going to explore the query editor, and in the database menu, I'm going to choose New York City Taxi. So my 2 tables will already be there. The week 3, which is the CSV one, and the glue_random hash, which is the Parquet one. So Athena is an interactive query service that you can use to analyze data in Amazon S3 with standard SQL. And before running queries, I need to tell Athena where to store the query results. So I choose Settings, Manage, and I can specify an S3 bucket for that task. In this case, I am just going to use the same bucket that I have as the CSV, but I am going to put the suffix /SQL. So once I hit save, I will be able to do queries. And if I go to the query editor and click on this icon here and choose preview table, it already populates for me select star from that specific table limit 10, which is the same query that you have in the exercise instructions. If I run the query, I will see that this query took 172 milliseconds to run. It went to S3, it got the data from CSV data, and it gave me the query result. So you can see that Athena is also pretty powerful. It can query data out of an Amazon S3 bucket. Now it's time to clean up the resources that we used for this lab. First, we are going to Glue, and we are going on the crawlers. And we're going to choose both of the crawlers we created, and we are going to delete the crawlers. Delete the first crawler and delete the second crawler. Once the crawlers are deleted, I am going to Tables, and I am going to delete the week 3 table and the Glue table. Delete. And notice that I am not deleting the data, I'm just deleting the table which points to the data. I'm going to the databases, and I am also going to delete the database. Now I'm going to the ETL jobs, choose the jobs, and I'm going to delete this job here, which is the New York Taxi Parquet. Delete jobs. Now I am going to Amazon S3 to delete the buckets that we created. I need to empty and delete the buckets. So I am going to empty this bucket. Empty. Just typing permanently delete. All right. And now I am going to delete the bucket. And also going to delete the bucket AWS Glue Assets. That's the bucket that has that Python script for the job, by the way. So first we are going to empty this bucket. We can delete the files, or we can use the option empty bucket. It's the very same thing. Now once the bucket is empty, the AWS Glue Assets bucket, I can finally go there and find that. AWS Glue Assets and delete the bucket. Delete the bucket. And last but not least, the CloudFormation stack that creates the role. So this is how we roll back everything and delete every single resource that we used for this lab. Hey y'all, congratulations! You've made it through to the end of Introduction to Designing Data Lakes in AWS. Good job learning about the basics of data lakes during week 1. You have a great showing in the AWS services involved for data lake operations for week 2. You continued to progress as you focused on data ingestion in week 3. And you finished strong this week, our 4th week, while looking to data prepping and visualization. If you've been keeping up with the readings and notes, you should be finishing this course with solid foundational knowledge of how to create and operate data lakes at scale in AWS. I hope this has shown you how powerful you can be by having domain over big data technologies, as well as inspired you to continue learning, exploring, and experimenting. Me and Morgan have definitely enjoyed bringing this content to you. I hope you enjoyed, and I hope to see you in the next class.